Welcome back for day 3 of the Integrated Distribution Systems and Planning Training. This event is sponsored by NARUC, NASIO, OMS, and the Grid Modernization Lab Consortium through U.S. Department of Energy, with my co-host here, Lisa Schwartz, being a huge part of this. So we're going to get started very momentarily. I just wanted to remind you, and I know I keep stressing this, but I will keep stressing it until our response rate is higher, a lot higher. We need you all to help us deliver the best trainings we can for each of these regions. So if you could please take a moment to fill out your surveys, and these evaluations really help us. The third day does include additional questions about the training overall, so please do budget a few more minutes just to answer those. But please know that we've adopted that feedback that you have into this training, and if you have ideas for other things or spin-off events, we've incorporated it into other trainings as well, and has really helped direct us as we help you all through this this new world here. So thank you for your time today, and I'm going to pass it back to Lisa and send you all those links to the surveys and to the presentations, which are located on the Lawrence Berkeley National Lab website. So Lisa.
Thanks, Carrie. Welcome to the final day of the training. Our theme today is demand flexibility. We'll start with net load shapes, what electricity systems need to serve in the presence of what we'll call load modifying resources at customer sites, and approaches for actively managing those loads. Then we'll dive deeper into how to use demand flexibility as a utility system resource. And next we'll hear about storage that includes technologies, services and valuation, participation in regional markets, and microgrids. And then we'll also hear about storage's role in integration of renewable resources and hybrid power plants, that is storage plus solar, wind, or gas. And we'll end the training today with a presentation on planning for electric vehicles and ways to manage electric vehicle charging. So let's get started. Chandler Miller from Lawrence Berkeley National Lab and Matt Leach from National Renewable Energy Lab.
Okay, great. Thanks, Lisa. Today, I'll be talking about the impacts of distributed energy resources on net loads and approaches for actively managing net load shapes before handing it over to Matt to talk about grid modeling. So let's go to the agenda. Next slide. Can we go to the agenda?
Hey, Carrie, this is Dominic. I've just lost connection, so if you could take over slides. That's very unfortunate timing, but I have lost connection to the webinar.
Okay, I will get that up and get your slides going.
Well, while we're waiting on that, today I'll be covering what net loads are, why they're important, the impact of a variety of distributed energy resources on net loads, both individually and combined. And finally, I'll talk a little bit about how utilities are starting to think about net load integration. And yeah, Carrie, just I guess let me know when you have those slides in control.
I am still working on it. All right, it's coming up. Are you able to see my screen?
Yeah, I can see your screen just fine, Carrie.
Okay, here we go, agenda, got it.
Great, so this is the agenda that I just discussed. So yeah, let's just go to the poll. we?
Carrie, is it possible for you to bring up the poll?
Yep, let me do that. Should be seeing the poll.
Okay, great. So our first poll question is, in 2018, what percentage of MISO system peak demand is equal to peak demand savings from demand response, where system peak demand was 123 gigawatts? So 10%, 7%, 2%, or less than 1%. So most of you got it right. The correct answer was C, 2%. Peak demand savings from demand response were equal to 2% in 2018, with about 1 gigawatt from both residential and the industrial sector, and half a gigawatt from commercial. So next slide. So let's start by, go up one, please, Carrie. Perfect, thank you. Let's start by defining net load shapes. So generally, net load shapes are defined as the profile of a customer's grid electricity demand over time as affected by behind-the-meter generation and other DER technologies. So while net load can refer to the total electric demand in the system, minus wind and solar generation, in this context, we're discussing net load of smaller aggregations of individual buildings, such as that observed by a neighborhood or at a feeder level. The importance of these aggregate net load shapes is that once you combine individual net load shape patterns, you begin to see characteristic shapes as a result of shared building consumption patterns. This allows a utility to better target desired impacts using DERs and understand what their impact could be on a particular net load shape. Next slide. And furthermore, the opportunity and need for net load management using distributed energy resources only continues to grow as variable renewable energy, such as solar, is further adopted. So even at low VRE levels, DERs provide an opportunity to control electricity load during periods of high system cost, such as the left side of the energy price duration curve shown here, where a small proportion of hours have exponentially increasing costs. And with more VREs, which can also be DERs, you have an even greater distribution of prices, both for the entire year and throughout a single day, which is shown at that bottom figure. This provides even more opportunity to shift load to periods with lower prices, such as with demand response, or use storage to dispatch VRE generation into higher price hours. Next slide. So go 2 down. Right there, perfect. And net load shapes are changing with increasing distributed solar. As shown by the top right figure, small-scale solar has more than tripled over the last 5 years and is projected to grow more as capital costs decrease within the US. As the bottom right figure shows, distributed solar adoption is not currently high in MISO, but emerging regulatory goals at the state, city, and utility level indicate that may change. As these organizations work towards decarbonization goals, solar penetration will inevitably increase. So next slide. So when thinking about the impact of DERs on net load, it's helpful to place their impact into a few different categories. And so the way we categorize that here is generation, such as distributed solar with or without batteries, energy efficiency, which provides ongoing reduction in energy use, load shifting through demand response and storage, which changes the timing of electricity use, load shedding, which reduces electricity use for a short time and typically on short notice. So shedding is typically dispatched during peak demand periods and emergencies, which is the way to think about that. And then we think about how these strategies work together to improve the net load curve overall. And so the graph on bottom, which I believe was discussed a little bit 2 days ago, kind of shows the different ways that those different impacts can actually affect the net load. So let's just go to the next slide. So now I'm going to present a few illustrative examples that demonstrate the different ways that DERs impact net loads. We'll cover solar, solar plus storage, standalone storage, efficiency and demand response separately, and then I'll discuss the impacts of combining them. Next slide. So starting with solar, the primary impact of distributed solar PV is lowering building net load through self-consumption and net export. Self-consumption offsets customer consumption from the grid through on-site generation, but once the site's net load reaches zero while solar is generating electricity, excess solar PV is exported to the grid. The figure here shows the increasing impact of adding solar to individual homes. While some homes with solar are exporting during midday, even during those low penetrations, it becomes evident as higher penetrations reveal a negative aggregate net load. And while I showed earlier that MISO solar adoption is low, the bottom right figure shows how shapes for other locations are beginning to appear in locations with high penetrations, such as Oahu, where 90% of installed solar was distributed as of 2014. While solar generation is not directly controllable, besides through curtailment, utilities can proactively manage its impact on net load in a few different ways. And some examples of that here are using late in day time of use peak periods to promote west-facing solar, thereby shifting its peak production time, changing solar compensation to promote different sizing of installations, establishing time of use rates that promote shifting of consumption to periods of higher solar generation, and promoting other technologies that smooth the midday curve, such as dispatch using energy storage, which I'll discuss next. So next slide. So when customers install solar and storage together, the midday peak can be reduced by shifting solar generation through storage to other periods when storage is financially incentivized to do so. Energy storage dispatch can be economic for a few reasons. Two primary reasons being one, scenarios where exporting solar is less valuable than shifting generation to other periods with positive net load. And the second being scenarios where time of use pricing enables the system to achieve a higher value by offsetting positive net load in periods with higher electricity prices. I should also say that here we refer to time of use rates as period-based pricing, where they vary based on time and day of week as well as season. So we're showing both cases separately in the figures on the right, where the top figure promotes energy storage dispatch through time of use pricing, and the bottom figure promotes dispatch through a lower solar export rate compared to the flat retail rate. So seen in the top figure, the time of use rate ultimately smooths the midday peak by charging solar to storage and then discharging only during the peak period. This creates a more significant net load reduction during the peak period as observed in the sudden load shift at 5 p.m. In contrast, the lower export rate in the bottom figure demonstrates a value of solar tariff, which is an export rate for solar that is separate from the retail rate customers pay for electricity. In this case, the value of solar tariff enables storage dispatch to always be more economic than PV export. What this ultimately leads to, first, is even more charging of storage from solar than in the time of use case, thus more midday net load smoothing. And the second, storage dispatching into all periods where there's positive net load. Next slide. And so what those previous cases show is that utilities can design rate structures that promote effective dispatch of energy storage, because energy storage behavior is quite sensitive to electricity price and rate schedule, as well as efficiency losses, among other technical parameters. So here we're showing a comparison of summer and winter behavior for an aggregation of 60 buildings with time of use pricing and net energy metering 2.0 in order to demonstrate other ways energy storage might behave. In cases where time of use pricing has a very low peak period, storage may actually be more economic to utilize grid charging instead of charging from solar at all, as shown in the top figure. This can even cause new net load peaks to form, which you can see here. Furthermore, solar generation is not displaced at all, despite the presence of storage. But otherwise, the use of time of use, or rather, the use of time of use pricing does not always promote storage dispatch. So for example, in the bottom figure, there is still time of use pricing, like in the summer case, but the difference in time of use pricing is too small and the incentive to dispatch is eliminated. So although the price differential is positive, storage must overcome round-trip efficiency losses in order to provide value through dispatch. What this ultimately implies is that rate design can be used to promote favorable storage dispatch for managing net loads, but it needs to also enable economic dispatch for a building system in order to be effective. Next slide. So what we've been discussing is how storage behavior is affected by volumetric electricity prices, meaning electricity charged by dollars per kilowatt hour. So let's go to the next slide. And so now what we're talking about is standalone storage, which is also being adopted by large commercial customers to minimize demand charges, meaning electricity is charged by dollars per kilowatt of electricity instead of by kilowatt hour. So in this case, when building demand is low, standalone storage charges using grid electricity. Then, when building demand is high, storage discharges in order to shave peak load. Since the goal of this type of dispatch is to reduce the customer's electricity bill, the time of discharge is dependent on when demand charges are high. So in this figure, you can see what this looks like in two common cases. So we have one case where customers are charged by non-coincident demand, meaning the time of building demand does not matter. And then in the second case, customers are charged by time of use demand, meaning the certain period of demand have higher costs. So for non-coincident demand charges, storage dispatches throughout the entire time of high building demand, causing a uniform peak shaving. However, with the time of use demand charges, which is that peak period range you see, storage only dispatches during the peak period. Since the storage system has a fixed amount of energy, the discharge during the peak is much deeper than with the non-coincident demand charges. But because storage waits to discharge until the peak, a large ramp occurs between the peak period and all other hours. So both of these structures have net load impacts that could be desired by utility, but their impacts certainly are not the same. So let's go to the next slide to kind of summarize storage. So now we've seen a few ways utilities can use energy storage to manage net loads. To highlight a few important takeaways, pairing storage with solar can help smooth midday net load and provide net load reduction during other periods. Standalone storage can accomplish this too, although grid charging can create new peaks. Regardless, rate structures need to incentivize economic dispatch, but utilities can use this to target when and how storage dispatches to maximize desired impact. And this could also include utilizing value of solar tariffs to promote higher self-consumption and less solar export. Okay, now that we've covered storage, let's go to a poll question before discussing energy efficiency. So in 2018, what percentage of incremental energy efficiency peak demand savings were from the residential sector? And the total peak demand savings from energy efficiency was 1 gigawatt. Okay, great. So most of you said 15%. The correct answer is 42%. So 42% of incremental energy efficiency peak demand savings were from the residential sector, with a majority of the other savings from commercial and a small amount from industrial. So we'll talk about why that's important next. So let's go to the next slide. Thanks. Or let's go down to energy efficiency. Perfect. So energy efficiency measures impact net load without active management. And while we historically think of energy efficiency as providing overall demand reduction, the timing is also important for net load management, such as targeting peak demand periods. So energy efficiency programs are used to upgrade common equipment in buildings, but different upgrades affect different time and seasonal periods of net load. For example, cooling will impact summer peak, while heating will impact winter peak, whereas other programs will reduce net load throughout the year. What's attractive about energy efficiency is that utilities can utilize this diversity of measures to strategically design programs to target reduction by period, season, and customer sector. Next slide. And so moving on to the first demand response strategy, time of use pricing provides net load management opportunities through customer responsiveness to price signals. So even without enabling technologies such as solar and storage, utility pilots have shown that customers consistently reduce or shift peak period consumption with time of use pricing. This was shown to be true for both opt-in and default options in multiple studies, but it also showed high retention rates in both cases. So for example, the figures on right show modeled net load based on customer response that was measured for a San Diego Gas and Electric pilot. An important takeaway here is that we're showing a time of use case that has 3 price periods. And those pilots show that in those cases, customers increased consumption during the off-peak, super off-peak slightly, but reduced their consumption during the peak. However, in time of use cases with the 2 price period, customers still reduced their peak period consumption while showing near 0 additional consumption during the off-peak. So let's go to the next slide. So in comparison to time of use, critical peak pricing provides more utility control by signaling peak days, which results in additional customer load reduction. So critical peak pricing works by charging customers a higher price for energy during a predefined period on critical event days, which are called infrequently throughout the year, typically 5 to 22 days depending on the program. For example, enrolled customers may receive a day-ahead notification, meaning the price they pay for energy the next day will include a much higher CPP period only on that following day. And they are incentivized to enroll through this slight price reduction for all other times, or rather they are incentivized to enroll because they receive a slight price reduction for all other times throughout the year. CPP prices are much higher than time of use prices, which where some of the lowest CPP prices are 4 times that of the off-peak rate, which ultimately incentivizes customers to have even more reduction. The figure here shows the modeled impact of CPP based on the percentage of customers enrolled, and a peak day is being shown because event days are called based on particularly high expected demand. So this is important because CPP enables utilities to manage net load during peak days at a deeper level than time of use. By applying an even higher price signal on those days, customers respond with additional net load reduction. Okay, so let's go to the final example of demand response on the next slide. Direct load control provides an additional layer of utility control by using load control instead of customer price responsiveness to reduce demand on peak days. With direct load control, or DLC, enrolled customers allow utilities to remotely cycle air conditioners and water heaters, as well as adjust thermostat settings during event days for pre-established periods. During events, equipment is cycled between 50 to 100%, or thermostats are adjusted by a few degrees to cause less HVAC usage. Like CPP, event days are infrequent and customers receive an annual credit for enrollment. The advantage of DLC is that it directly targets equipment responsible for driving that peak demand. And by controlling it directly, the utility can better estimate the net load impact. So the bottom figure actually shows the top 10 utilities in MISO with the highest enrollment, as reported by EIA, where many co-ops already have high enrollment of DLC programs. And so there are additional demand response programs besides the 3 I've just shown. I think there's a table for that on the CPP slide, but these provide an idea of how demand response can be used to impact net load on a distributed level. So let's go to the next slide. So by combining DERs, utilities gain a menu of options for managing net load through generation, shift, and shed. So this is enabled by DERs acting in concert, and certain scenarios show how DER behavior is enhanced by the presence of other DERs. So for example, the figure on right shows different aggregate net loads for a peak summer day with time of use pricing, where 100% DER customer adoption is assumed, but with different DERs actually applied. And so what I want to particularly draw your eyes to here in these figures is the comparison of the case that has CPP, PV, and storage compared to the case that just has PV and storage. And what this is showing is that by the additional price signal from CPP, the storage actually behaves a little bit differently. Whereas without the CPP price signal, storage would have dispatched only during the peak period from 5 p.m. to 8 p.m. With CPP, storage actually starts to dispatch as soon as there's any positive net load, which is at 3 p.m. And what that does is storage actually starts to aid CPP in reducing peak demand. And while this figure is only one illustrative case, it demonstrates how DERs can impact net load simultaneously in different ways that can, in some cases, enable each other. So let's go to the next slide. Looking forward, utilities are beginning to design platforms that tap into DER flexibility through heightened visibility and control over DERs. A great example of this is in California, where state regulatory design is enabling a platform-ready grid. So in California, Rule 21 requires all distributed solar to use inverters with remote communication and grid service capabilities. And while platforms are still developing in California, This allows distributed solar PV installations to be pretty much platform ready so that utilities can control them without requiring additional technological upgrades. Additionally, there was a bill passed in 2019 in California that will foster higher adoption of demand response ready appliances by effectively incentivizing smarter appliances to be adopted in customers' homes. So these regulations enable technologies that will ultimately provide utilities with more visibility and control. On the utility side, some utilities are creating centralized platforms for aggregating dispatchable DERs to control net load, such as virtual power plants that can potentially operate DERs synchronously, provide grid services, and participate in wholesale markets. So kind of like how we talked about direct load control, VPP would enable utilities to schedule and dispatch other DERs, such as energy storage systems. And furthermore, they can aggregate these smaller resources, such as small storage systems in residential homes or even commercial, which facilitate sort of a unified approach to providing demand response and other grid functions for greater impact. And so I've provided some examples of utilities that are testing VPPs through pilots here, and there are a few links there. And then on the next slide, we can go to, I've provided some more questions that states can ask. And then on the following slide, I've provided some references that are useful context for what I've just presented here. So with that, I will hand it over to Matt. Thank you.
Thanks, Chandler. So hi, everyone. I'm Matt Leach from the National Renewable Energy Lab. And today I'll be talking about integrating load shape analysis into grid modeling. Next slide. So there are three main objectives that I want to cover. The first step in estimating the demand flexibility that buildings can provide to the grid is to understand building energy consumption at scale. And by that, I mean capturing realistic building load profiles and variability in energy use across and within different building types. Next, perturbation of control set points, either random or corresponding to specific flexibility dispatch scenarios, such as load shed or load shift events, can be used to characterize flexibility potential by building type and end use. And finally, grid models can be employed to optimize the dispatch of the available flexibility or to quantify the net impacts of specific dispatch strategies. Next slide. Okay, so what are the key takeaways of this presentation? First and foremost is that demand flexibility should be treated on par with supply side options, so the associated grid impacts and benefits, including operating cost reductions, can be quantified and monetized. And second, DOE and the national labs, including NREL, are developing new tools and analytics to account for the full economic impact of demand flexibility, variability in value based on time and location, impact of distribution system savings on transmission and generation system value, variability in value due to interactions between DERs and between DERs and other system resources, and life cycle analysis for demand flexibility. Next slide. So you've probably seen some of this information in other presentations, but it's important to keep in mind the benefits associated with developing programs around the potential for buildings to provide demand flexibility. Some of those benefits include reduced grid congestion, especially during peak demand periods, reduced energy bills driven by reduced infrastructure costs, minimizing curtailment of renewable generation, and enabling lower electricity costs by reducing grid operating costs. Next slide. So as I touched on previously, understanding building energy consumption is the foundation to any estimation or utilization of building demand flexibility. So first, we need to understand where energy is used across the US building stock, where geographically, in what building types, what end uses, and at what times. Next, we need to understand how those buildings can provide service to the grid. What is the role of efficiency in providing that service? What is the capacity for load shaping? And what are the time, location, and configuration dependencies? Once we can answer these questions, we will have the necessary foundation for demand flexibility estimations, and dispatch strategies. Next slide. To answer these questions and to package those answers into powerful and flexible analysis tools, NREL has developed ResStock and ComStock, which are bottom-up engineering models of the US building stock. ResStock covers the residential stock and ComStock covers the commercial stock. These tools have been developed to achieve a balance between speed and complexity. They are highly granular to capture diversity across and within building types. They are calibrated to real data at the sub-hourly level. They can model controls and demand response strategies. They enable scenario analysis for both efficiency and demand response and account for interactions between potential measures. And they provide visualizations for slicing and analyzing data. Next slide. The next few slides provide a brief introduction to the ResStock and ComStock tools. At their most basic, these tools combine a database of building stock characteristics with physics-based modeling and high-performance computing workflows. Next slide. They are built on databases made up of large public and private data sets. In total, there are over 6,000 probability distributions for more than 100 parameters organized in a complex dependency tree. On the right side of the slide here, you see an example of how these parameters are nested. You can see for a particular building type, there are distributions associated with vintage, floor area, and footprint, where each distribution is tied to the selection from the last. Next slide. The models themselves are built up using the DOE tools OpenStudio and Energy Plus, and they enable detailed sub-hourly energy simulations with breakdowns by end use. Next slide. And all this granularity and detail requires significant computational power. To model the full residential and commercial stock requires about 800,000 annual energy simulations. To facilitate this, ResStock and ComStock are designed to leverage supercomputing resources, including Amazon Web Services, and are built around a big data technology stack. Next slide. As ResStock and ComStock are bottom-up models, calibration is critical to ensure accuracy at scale. This is where the end-use load profiles project comes in. For these tools, ResStock and ComStock, there are different scales of analysis and also different scales of data collection and calibration. And while it is important to have parameter distributions that map to the national scale, it's not possible to collect highly granular characteristic data in every region, and even if we could do that, it would not be practical to calibrate to all those data. Next slide. In light of those constraints, the end-use load profiles calibration approach is defined as follows. First, compare results to widely available data, including EIA annual electricity sales data, for example. Second, study regional transferability of non-weather dependent end uses to find opportunity for extrapolation of specific calibration exercises. And finally, perform enhanced calibration for 5 specific regions for which we have AMI data and consumer metadata, and then extend those results to the extent possible. And the bottom line underlying all this work is the guiding principle that model inputs will only be changed when supported by data. Next slide. This slide summarizes the types of calibration data being collected and the source of those data. I won't go into detail here, but you can see the main types of data are utility sales, aggregate load shapes, AMI data paired with characteristic metadata, and submeter data. And the sources of these data are extensive and range from public to private. Next slide. I think we'll answer the poll question now. So the question is, in my state, demand flexibility is considered for use in, select all that apply, achieving energy, demand, or air pollutant reduction goals, achieving a renewable energy goal, integrated resource planning process, distribution system planning process, or shaping energy efficiency or demand response programs. Okay, it looks like the most popular answers were shaping energy efficiency or demand response programs, integrated resource planning process, and achieving energy demand or air pollutant reduction goals. Okay, next slide. So I've talked about, oh, back one, please. I've talked about how Revstock and Comstock can be used to create building portfolios that can then be simulated to generate aggregate load profiles to capture various scenarios. And in the context of demand flexibility, these tools can be used to explore how different packages of efficiency and demand response measures can be used to characterize the demand flexibility potential of specific combinations of region, building type, and end use. So next I want to talk about how the resulting demand flexibility estimates can be packaged as inputs for grid modeling analysis and how that can be useful. And you'll notice that, oh, sorry, go back to this previous slide, thanks. You'll notice that the following discussion is based on analysis that we've done at the bulk power scale, but the concepts demonstrated here apply to the distribution scale as well. And it's important to note also that there are multiple ways to incorporate building demand flexibility into grid modeling. The most sophisticated approach is to represent demand flexibility using a virtual battery or virtual storage and generation model with time-dependent storage capacity and charge and discharge rates. In this scenario, which is presented here and in subsequent slides, flexibility is dispatched by the grid model along with supply-side generation in an optimal way to minimize overall system cost. This enables us to measure the maximum value of the resource and accounts for dynamic interaction between flexibility and generation. A simplified approach could be to optimize dispatch using price data generated by the grid model and then feed the net load impact of that optimization back to the grid model to evaluate the resulting change in operating costs. This simplifies the inputs to the grid model, but assumes that flexibility dispatch won't substantially impact electricity costs. An even more simplified approach would be to skip optimization altogether and simply apply discrete demand response scenarios to the building stock models to determine the net load impact and then feed the corresponding net load shape back into the grid model. Next slide. This slide shows how all these parts and pieces can be combined into an iterative, self-validating workflow. First, starting in the lower left, Revstock and Comstock are used to generate building portfolios and perturb those portfolios to characterize demand flexibility potential. Next, surrogate modeling and aggregation methodology are applied to develop virtual generation and storage models for flexibility by end use. Those models are then fed into grid modeling analysis that optimizes their dispatch, and the resulting dispatch signals can then be fed back into the building portfolio models to close the loop by verifying the extent to which the intended dispatch can be achieved. Next slide. The last thing I want to talk about is how demand flexibility resources can be categorized and how those categories map to specific aggregate model representations. Currently, we group demand flexibility resources into 4 categories: schedulable resources, high thermal capacity storage resources, standard storage resources, and sheddable resources. Each of these resource types has unique characteristics that shape how it can provide service to the grid. Schedulable resources are those that can be moved throughout the day without resulting in a reduction or loss of service. These typically have little or no environmental coupling. An example would be pumping for an irrigation system. High thermal capacity storage resources are typically set point driven and exhibit moderate environmental coupling. An example would be a refrigerated warehouse where you would have a very high thermal capacity and likely be able to float for some time to provide a load shed or load shift. A standard storage resource is similar, but of lower capacity and typically more strongly coupled to its environment. Examples of this would be space heating or cooling. And sheddable resources are those that can be turned off, but doing so is tied to a direct reduction or loss of service. Examples would be lighting or ventilation. The unique characteristics of each of these resource types map to different configurations and parameter definitions for their respective virtual storage and generation models. The remaining slides go into detail on how these resources can be modeled as aggregate inputs for grid modeling analysis. I included them here for completeness, but we'll just touch on them briefly in the interest of time. Next slide. So here we see agricultural pumping as an example of a sheddable resource. In the plots on the right, the magnitude of the resource is presented according to energy service, either energy, contingency, or regulation, and availability can vary by season and also by hour of the day. And in this particular case, you can see that the magnitude of the resource is highest in the summer and spring, as you would expect, and significantly lower in autumn and 0 in the winter. And you can also see that the magnitude of the resource is the same across all grid services in this case. Next slide. So here we see commercial heating as an example of a storage resource. In this case, the magnitude of the resource is highest during winter months when heating is needed and close to 0 in the summer. You can also see that availability dips during morning hours when heating is needed to bring space temperature up to occupied set point. It's also worth noting here that this type of resource can provide the highest benefit to the energy market, down to almost no benefit to the regulation market. And this is because the time response associated with passive thermal energy storage is relatively slow. Next slide. And last, we see commercial ventilation as an example of a sheddable resource. The magnitude of service it can provide to the energy market is 0 in all cases because its generation is restricted to 0. And this is because the dispatch of the resource corresponds to an absolute loss in service. And as such, we assume that it would only be used to provide contingency service for only a very small number of hours per year. Next. So thank you very much for your time, everyone. If you have any questions about the tools and workflows we're developing at NREL and how you can leverage them, please don't hesitate to reach out to me. Thanks again.
Thanks, Matt. Thanks, Chandler. We have a few minutes for questions. Let's get started with one for either of you, actually. Do any tools exist that you're aware of that can help regulatory agencies design time of use rates that effectively promote beneficial storage behavior? And we also have a storage panel later, so I have other questions we can punt to our later storage panel if you like.
So one example I can think of is that the grid modeling workflows can be used to generate basically hourly price values that correspond to basically the dispatch of supply side generation to meet load. And that can be done for various different scenarios. And those price signals can be used to run various dispatch optimizations, whether that's for storage or for DERs. So you could think about things in that way, where you're sort of optimizing your storage dispatch to a price signal or vice versa.
Mm-hmm. And certainly what we use for a lot of our work for this and some other work we've done is DERCAM, which is LBNL's tool that you can build electricity rate tariffs that the tool will respond to with, like Matt was saying, sort of a optimized storage dispatch, and then also with some sort of cost variables and cost outputs. And we use that in the behind the meter sense, but rather than optimizing the electricity rates, it's more used as a tool for providing electricity rates and looking at sort of what that output looks like.
Yeah, and that's a publicly available tool, so get in touch with Chandler or me if you want more information for that. We found it pretty easy to work with and pretty good at reviewing a real variety of tariff designs. I think we have time for one more question if we get some quick responses. How can, Chandler, this is for you, how can utilities think about active management of solar and storage if they don't have direct load control?
Right. What I've talked a little bit in this presentation is ways that utilities can, like we were just saying, design electricity rates that sort of influence that the behavior of solar and storage. But also one reason, kind of at the end, we talked about virtual power plants, is it provides sort of a further level of visibility and control for actually kind of incentivizing customers to allow utilities to take further control of their systems as long as the right infrastructure and sort of cost incentives are in place.
Great. Well, thanks so much. I think that's time. So Carrie, turning it back to you for the next session.
Thank you.
Thank you.
Thank you both. We are getting up Natalie Frick. She has a background in energy efficiency, and today she will be talking about demand flexibility as a utility system resource. Natalie, are you able? Yep, you're there. Okay, great.
Okay, and can you hear me okay?
You're great.
Okay, perfect. Thank you. Hello, everybody. Good afternoon, or yeah, good afternoon, I think, to everyone. I'm Natalie Frick, and I'm with Lawrence Berkeley National Lab, and today I'm going to talk about demand flexibility as a utility system resource, and I'll be building on conversations or presentations that you've heard thus far. So the agenda that I have today, I have 5 different topics that I'm going to talk about, and my first topic is what is demand flexibility and why is it important? And my third one is examples of technologies that promote demand flexibility, and I'll just cover that one pretty quickly. And then I'll move on to opportunities and examples for states and utilities to advance demand flexibility. And then I have some resources for more information, but I'm not going to focus on those. I will just have that available for you. And I do want to thank several people who helped contribute to these slides: Lisa Schwartz, Tom Ekman, Steve Schiller, and Jared Langevin, all from LBL, helped out with lots of this content. So we can go on to the next slide, please. Yeah, we can actually keep going. What is demand flexibility? So demand flexibility is the capability of distributed energy resources, or DERs, to adjust a demand profile across different timescales. And DERs are efficiency, demand response, or DR, DG, distributed generation, storage, electric vehicles, and combined heat and power. And I'm not going to spend a whole lot of time on this slide because several other presenters already talked about what demand flexibility is. So you can refer to those presentations if you'd like more information, or look at Building Technology Office's Grid Interactive Efficient Buildings. They have lots of content and resources there. So we can go on to the next slide, please. So we know what demand flexibility is, but how do we value it? Traditionally, the value of DERs has been determined by using avoided cost. However, the methods used to establish avoided cost vary widely across the US due to differences in markets, resource options and their costs, and policies and regulatory context. And then some states provide detailed guidance regarding specific types of analysis required. So some jurisdictions will use market-based valuation, while others will use resource planning processes. And some use time-sensitive valuation, others don't. And some consider the value of avoided T&D, transmission and distribution, and some don't. So there's a wide breadth of different processes being used. The economic principle of this approach is that the value of a resource can be estimated using the cost of acquiring the next least expensive alternative resource that provides comparable services. And the value of demand flexibility can be determined in the same way. You just need to make sure that you're considering it along with your other resources in the same way. Next slide, please. So there's many different value streams that have to be considered when valuing demand flexibility, including time, location, grid service, the expected service life, and the avoided cost of the next least expensive resource alternative. And the economic valuation of demand flexibility for grid services should be established through a planning process that considers all of these different factors. Next slide, please. So why is demand flexibility important? We can go on to the next slide. I think some of you who took the poll in the last presentation indicated that you use demand flexibility for a variety of different processes, including integrated resource planning and state energy goals. So you probably already know that it's important because the electricity system is changing as our state energy goals. The electricity mix in MISO has changed significantly since 2005, which is what this chart on the left shows, which is retirements. In 2005, about 80% of MISO's footprint was generated from coal, with a very negligible amount coming from renewables. And today, less than half of the region's total energy comes from coal, with about a quarter of it coming from natural gas and about 7% coming from wind, with lots more renewables coming online. And about 3/4 of retirements since 2005 that have been approved are from coal, which is what these dark gray bars show in this chart on the left side. And on the right side, these circle pie chart is what MISO anticipates generation will be in 2030, and about a third of it is going to come from renewable energy. And then this last chart that's down on the bottom is from MISO, and it's what MISO anticipates the hourly ramp needs are for a portfolio that's comprised of 20% wind and 20% solar. So as the grid changes, the way that it's operated is also going to need to change, and demand flexibility can help with that. We can go on to the next slide. Thanks. DERs and demand flexibility need to be in the right place and the right time to meet grid needs. And this slide shows the range of annualized local distribution avoided costs by area using California utility distribution planning information. And the research demonstrates that there's high value locations across the state, but that the DERs or demand flexibility have to be targeted if you want to capture that highest value. Next slide, please. Demand flexibility can provide a variety of different grid services, and I think you've already heard about this from some other presenters as well. This includes energy, capacity, ancillary services, non-wire solutions. And the value associated with these grid services includes avoided or deferred costs associated with fuel and operating and maintenance, T&D equipment upgrades, etc. So we can go on to the next slide. And then finally, as some of you have already identified, demand flexibility can help you meet your state energy goals. There's many states in the Midwest and MISO's footprint that have established energy efficiency and renewable energy standards or goals and are considering additional provisions. And some states focus on DERs. In Michigan, the Renewable Portfolio Standard offers a 2x multiplier for solar. And several states have introduced legislation that have open dockets or have open dockets that are discussing storage. Next slide, please. So I'm going to briefly talk about technologies that promote demand flexibility along with energy efficiency. And I'm going to focus on the ability of demand flexibility to help out the utility grid. So we can go to the next slide. I know that you've already heard about demand flexibility technologies, and you've heard about how different DERs can provide distribution system value. And so this slide and the next one have a little bit of different content on it. This table that's in the middle has demand flexibility measures and the approach that was used for this study that I'm going to talk about the results from it. And this slide is for residential, and the next slide is for commercial. And the demand flexibility measures are what were used to produce the charts that are on the right side of the slide, which the top one is for January and the bottom one is for August. And this is from a recent study that was done by LBNL and NREL. And the charts show the dotted line in the charts. This is for Rochester, Minnesota. There were several other regions looked at, but I wanted to focus on the MISO footprint. The dotted line shows the baseline without any intervention from technology. And as you look at the other colored lines that show up, there's a green one that is demand flexibility and energy efficiency that's combined. Excuse me, that's what the red line is. The green line is just demand flexibility. And the blue line, I believe, is just energy efficiency. And so you can see in this pink shaded period, that's the peak period for this residential house, that when you combine energy efficiency and demand flexibility together, you're significantly reducing below what that baseline was you're reducing energy consumption during your peak period. So that's very beneficial. And it's happening in both the winter and in the summer. So we can go on to the next slide and I'll show, so the measures that were considered are water heating, thermostats, clothes washers and dryers and dishwashers, pool pumps and electronics. So a variety of different measures that are providing both efficiency and demand flexibility. And then, yeah, for commercial, so this is the same chart, so the same table in the middle with demand flexibility measures, and then in our charts, this is instead of a residential home, it's a medium office. And again, the dotted line is what the baseline energy load is without any interventions, and then the different colored lines represent combinations, the combination of efficiency and demand response, and then efficiency and DR alone. And again, as you can see in that pink shaded period, that's the peak period in the summer and the winter, efficiency plus demand flexibility are providing the greatest reductions and the greatest benefits to the grid. If you're looking at the kind of purpley bluish period that's during the beginning of the day, that's when you would want to increase consumption. You can see that demand flexibility is going to be more beneficial there than demand flexibility alone is going to be more beneficial there than demand flexibility plus efficiency, but that's for consuming electricity. So, and then the measures that were considered here were lighting, plug loads, global temperature adjustments in the building, pre-cooling, and ice storage. So we can go on to the next section. So this section and the next section both talk about opportunities for states to advance or promote demand flexibility. The next few slides are really focused on some research that LBL has done on demand flexibility and grid interactive efficient buildings that are part of a C Action Report series. And so we can go to this first slide. This is a summary of key actions that state and local governments can take to advance demand flexibility. And we've grouped them together into three broad categories: gathering information and identifying opportunities, developing and implementing strategies to integrate demand flexibility, and accelerating adoption. And as this table shows, both the Public Utility Commission and state energy offices can implement the majority or all of these actions. So for example, commissions can specify consideration of demand flexibility in utility planning processes such as distribution planning or integrated resource planning. They can enable participation of demand flexibility in procurement for grid services, authorize pilot projects. They can also convene stakeholders to have informal or formal conversations about the role of demand flexibility as a resource. And then if you're interested in more of what this report offers, I do have the link at the bottom of the slide. And my next two slides focus specifically on this accelerating adoption portion of this table. So the last portion, specifically the two middle rows in that section, which are on evaluation and measuring performance. So we can go to the next slide. This is a second of three reports that we have in an LBL C Action series. That there's the link available for this one. This is focused on valuing demand flexibility. And I briefly talked about that at the beginning when I was talking about why demand flexibility is important. And as we all know, when you're comparing resources, grid planners and regulators have to know the value of what that resource is. And so this table is a summary from the report, and it shows opportunities for states to update their economic valuation methods for DERs that provide demand flexibility. And the enhanced valuation methods apply to distribution and generation and transmission planning. The first step before you even get to updating your economic valuation methods is to consider what your current methods are and assess and compare them to what these enhanced methods are that we're suggesting and are shown in the table. And then after that, a utility or regulator can work on prioritizing which of these enhancements are going to be most beneficial to them and what the cost for making that enhancement is, both in terms of time and all of the changes that might be necessary, and consider what's going to be the most important and move forward accordingly. And some of the enhancements are more applicable to specific parts of the system than other parts. So that can also be a factor as states are considering how they can promote demand flexibility. We can go on to the next slide. So this is the third report in the series about that provides opportunities for states to promote demand flexibility. And this one was on establishing practices for robust assessment of demand flexibility performance. So state and local governments can play an important role in this to support reliable and cost-effective performance assessments of demand flexibility. And again, the link for this report is at the bottom of the slide. There's a variety of different types of actions that states or local governments can take, including encouraging performance assessments, providing technical assistance and sharing the results, and this could be leading by example in public buildings, adopting current best practices for demand flexibility assessments, which could include supporting standardized protocols for demand flexibility assessments, or ensuring consistency in the evaluation of DERs and their demand flexibility attributes, supporting advances in assessment practices, which could happen through pilot projects, improving access to data from existing and future utility infrastructure. So this could be about data access provisions or cybersecurity, privacy, or interoperability standards. And considering improvements in demand flexibility infrastructure, this could be through sub-metering or encouraging demand flexibility ready equipment through codes and standards, which Chandler touched on a little bit during his presentation. So we can go on to the next slide. So there's lots of different examples of states and utilities encouraging demand flexibility or a component of demand flexibility today. And I'm going to talk about some of the opportunities and couple it with examples. There's a variety of different implementation levers that states can pull. And the ones that I'll talk about in this section are resource standards, efficiency and demand response programs, rate design, performance incentives, executive actions and state energy plans, and building energy codes. And I'll talk about each one of these in a little bit of a higher level and then focus in on some of the examples that I have to share. So we can go on to the next slide, please. So the first group that I mentioned are resource standards, and states can use resource standards to promote DERs, including efficiency and demand flexibility. And the Massachusetts Clean Peak Standard is probably the most well-known standard that is promoting demand flexibility right now. And I'm going to talk about that more on the next slide. So other examples for including peak demand reduction targets as part of energy efficiency resource standards. You can include peak demand reductions as part of energy efficiency resource standards, or in lieu of that, requiring utilities to acquire all cost-effective efficiency, or using the time-sensitive value of efficiency. So we actually, if we could go just back one slide to the Massachusetts Clean Peak Standard example. Thank you. Okay, so this is an overview of the standard. There's a lot more to it than what I could put on this slide. So the standard was passed in August, and the goal of it, some of the goals of it were to create a reduction in peak electricity demand and reduce emissions. And the standard requires load-serving entities to meet 1.5% of eligible retail sales with clean peak energy. And the percent increase is 1.5% a year up to 46.5% by 2050. And the peak period changes by season, which is what this table on the top right side of the chart shows. And the hours for peak performance are changed by season. And there is banking with this, so load-serving entities can bank up to 30% of their clean peak energy for up to 3 years. So resources that are eligible for the standard are listed in the third bullet here on the slide: new and existing renewable energy, demand response, qualified storage that's charged from renewable energy. And so the energy storage charging periods are what that table on the bottom right side show. So if you want to use storage to meet the standard, you have to charge it predominantly with renewable energy and charge it during these windows. Let's see, there is a multiplier for credits, including a 25x multiplier if the resource is generated during the hourly monthly system peak. So it's a pretty big bonus for load-serving entities that can achieve that. Okay, we can go on to the next slide. So this is my second type of examples, which are energy efficiency and demand response programs. So for efficiency, there's a couple ideas. States can integrate efficiency with DR, and there's increasing examples of states or utilities or regulators really trying to actually get efficiency and demand response integrated. And I have a couple of those examples. Ameren, Missouri has a peak time rebate program that provides efficiency savings from a smart thermostat, and then automatically enrolls the customer in a direct load control program. So it just kind of combines the customer acquisition cost for those two programs. Pay for performance programs are also a way to encourage demand flexibility or energy efficiency savings during peak time. Okay, so demand response programs, it's the change in rate of electricity consumption in response to price signals or a specific requirement of a grid operator. And the utilities and markets offer demand response programs that can help customers reduce their bills and provide grid services. Automation and aggregation are ways that can really help simplify participation. In MISO, there's lots of direct load control programs or other demand response programs that shed load, but there's not that many that are shifting to different times of the day to achieve state or utility goals at this time. And then this last bullet is about MISO's demand response programs, and I'll talk about that more on my next slide, but generally they can be grouped into economic and emergency program offerings. We can go on to that slide. Thank you. So as I mentioned, emergency and economic demand response. This table describes the demand response resources and the capability for each one of those resources over the last 3 years. And this is from MISO's independent market monitor. The majority of demand response in MISO is that's participating is an emergency resource. And that is the first 2 rows of the table and the bottom row of the table. For some reason, I didn't put them together. But MISO can only deploy emergency resources when they have declared an emergency. So load modifying resources, the first 2 rows of this table, are planning resources that are obligated to curtail during an emergency. And these are typically interruptible load programs or direct load control programs that are administered by load serving entities. And they also include behind the meter generation. And then emergency DR resources, which is this last row of the table, are not obligated to curtail during emergencies, but if they do participate, they do curtail, they're compensated at the greater of the prevailing real-time locational marginal price or their offered cost for verified demand reductions. And then the kind of middle rows, the DRR is demand response resources, and they're capable, there's a very limited number of them, and the vast majority of them are in the first type of demand response resources. And about 1/3 of all of the demand response resources that came online were in the second half of last year. So this is still kind of an emerging service that is being offered, and there's not that many resources in it quite yet, but MISO does anticipate that this is going to be ramping up. In 2019, there was 41 demand response resources that were active, and with most of them coming online in the latter half of the year. Okay, so we can go on to the next slide. This is really focused on an example of a state participating in a demand response market. And this is from Massachusetts, where the Division of Capital Asset Management and Maintenance works with a third party they have a contract with a third party to provide services for state-owned facilities for active demand capacity resources and on-peak demand resources, and then also their capacity tag. And the capacity tag is reducing the demand charge for the facility, which results in year-long savings. And then the other 2 active demand and on-peak demand resources participate in ISO New England's market. So Massachusetts estimates that it's saving about $500,000 a year in energy costs for its state-owned facilities that participate in this program. So it's very beneficial to them. Let's see, next slide, please. Thanks. So my next 2 slides are on utility demand response programs, and this one is from Vectren, which is an investor-owned utility in Indiana. IPL, also an IOU in Indiana, has a similar program. This is a direct load control program that customers participate in, and they can override. The last evaluation that I looked at was for 2018 performance, so it was from last year, and it evaluated the impact of 2 different performance windows, which is what these charts show at the bottom of the slide. So between 2 and 4 p.m., which is the majority of the events that were called, and between 4 and 6 p.m. So in 2018, Vectren called 10 events in July, August, and September, and most of them were in the 2 to 4 period. 2 of them were in the 4 to 6 period. And during the events, the homes are pre-cooled for an hour, and then the set point is raised 3 degrees. And savings, you can see this in the charts at the bottom, we're about 1 to 1.5 kW per hour per participating thermostat, which resulted in about 860 kW for the first hour and about 970 kW reduction for the second hour. We can go on to the next slide. So this is a direct load control program from Entergy in Arkansas. And it's a little bit different than Vectron's, which is why I featured it here, because it has a bring your own device aspect of it, and it also has a sliding scale of incentive payments based on if customers opt out or not. So in Vectron's program, the customers, I believe, receive the incentive regardless of if they opt out, and Entergy tweaks that a little bit so that if customers opt out of 4 or more events, they don't get any annual incentive. But so this first bullet should actually say that the events can occur between noon and 7, not the entire time. And so in that window, a signal is sent to a thermostat, and that increases temperature in the building. And the events usually last about 4 hours, and they won't occur for more than 3 consecutive days. And you can bring your own thermostat, or you can obtain it from Entergy from this program, or you can obtain it from a different program that Entergy offers, and that's the initial incentive. And then for each year that you actually participate and don't opt out of more than 4 events, residential and small commercial can receive different incentive levels between $40 for residential and $100 for small business. You can go on to the next slide. So my third example of states and utilities using or starting to use demand flexibility as a resource is rate design. And some opportunities are that states can offer time-based rates with a large differential between them, between on and off peak rates, or they consider rates that are more reflective of hourly system prices. Also, utilities can design rates that are opt-out instead of opt-in, and that usually results in higher participation by customers. And for commercial customers, utilities can establish demand charges that are during the peak demand periods, or have a higher charge that are during the peak demand period for the system. And I have 2 examples of time-based rates in the next 2 slides, so we can go on to those. My first example is from Minnesota, and the PUC approved Xcel Energy's residential time of use flex pricing pilot in 2018, and it'll be launched next month. And Xcel anticipates offering the pilot to about 10,000 customers in 2 different cities. And the graphic that's on the right side of this slide shows the pricing. And there's a pretty large differential that promotes customers shifting their usage to the off-peak or lower cost hours, which are between any time except for 3 to 8 p.m. And so prices are the highest in the summer and the winter, and they're about 2.5 times higher from 3 to 8 p.m. in the summer and winter than they are from 6 a.m. to midnight for all of our other hours during the day. And then they're about 6 to 8 times lower if you are using electricity between midnight and 6 a.m. Xcel also filed a proposal to revise its general time of day service rate for non-residential customers. And the PUC directed them to propose a rate to be more reflective of hourly system costs and to send price signals that would reduce peak demand and increase system utilization. And the rate's going to be mandatory for Xcel's larger general service customers, and it'll be optional for all other general service customers starting in 2024. And Xcel would like to pilot this with a limited number of participants focused on people who have electric vehicles. And that's a work in progress still. So we can go on to the next slide. My second rate example is ComEd in Illinois. This is their hourly pricing program, and Ameren also has a very similar program that's called the Power Smart pricing. So customers choose to participate in this rate, and it gives them access to hourly PJM wholesale market prices. And participants can shift their usage to reduce their bills, including shifting their usage to when pricing is negative. ComEd offers customers lots of resources to make sure that they're not experiencing higher bills, including participation in a direct load control air conditioning program, hourly pricing alerts, and lots of different kind of communication and an online platform for looking at what the prices are. And then they also have this feature called Load Guard, which is a program that moderates air conditioning usage during summer months during high-priced hours. So it'll put your air conditioner in conservation mode for a couple hours when prices spike up really high. Okay, we can go on to the next slide. So states can use performance incentives in a variety of ways to encourage demand flexibility. I have a couple examples here. They can provide an incentive for utilities that meet peak demand targets with DERs, including efficiency. And another option is to create performance metrics for the utility to develop opportunities for customers to align their loads with grid needs. Can go on to the next slide. I have another example from Minnesota here. So the commission opened a docket to look at performance metrics that are aligning load with resource generation and reducing peak demand. And they approved these metrics for Excel earlier this year for demand response shedding, and they identified future metrics for shifting and shaping. And in the order from earlier this year, the commission directed Excel to provide data and examples of shaping and shifting metrics to interested parties, and then to work on a timeline for implementing those metrics in the future. And I think that those workshops are happening this month and next month. So those are still being developed for the future metrics. We can go on to the next slide. So states can use executive actions or state energy plans to advance demand flexibility as well. So there's two examples I have on this slide. The first one is from Illinois, where the governor released principles for clean and renewable energy, including giving the commission the ability to create standards for controlling demand on the grid and optimizing utilization of electricity grid assets. And in New Jersey, 2 of the 7 strategies in the energy plan that was released last year to achieve the state's goal of 100% clean energy by 2050 include demand flexibility. The first one is around managing and reducing peak demand. And then the second one is on modifying rate designs to empower customers' energy management and align utility incentives with state goals. So we can go on to the next slide, please. So my last example of actions or opportunities that states are taking is building energy codes. And states can use codes in a variety of ways. Starting from my bottom point on this slide, California required commercial buildings to be demand response ready in their 2019 code, which I believe Chandler touched on, and allow residential buildings to use efficiency, demand response, thermal, and energy storage to reduce the size of mandatory PV systems from their most recent code for residential buildings. And then also in 2019, California passed a law requiring the CEC to establish standards for cost-effective deployment of flexible demand technologies for appliances, and that is an ongoing proceeding as well. So we can go on to my next slide. So these are questions that states can ask as you're considering how to use demand flexibility or other DERs, including efficiency. As a grid resource, you can think about what goals can demand flexibility advance, and then how can your state policy or regulatory gaps be filled to advance your demand flexibility and enable demand flexibility to be a grid resource. Valuation, performance, measuring performance, those were a few that I talked about earlier, incentive mechanisms, rate designs. These are all different options that I talked about in the slides. So we can go on to my next slide, and this is my last one. So there's quite a bit of time left for questions if anybody has any, but in addition to all of my other suggestions that I made, states can also join the NASIO Grid Interactive Efficient Buildings Work Group. The Department of Energy funded national labs to provide direct technical assistance to this working group, and we're helping states identify opportunities to advance demand flexibility in their state. And currently we're working on technical assistance, including advancing publicly owned grid interactive efficient buildings and quantifying the potential for grid interactive efficient buildings, and identifying and overcoming challenges for states to creating pilots for grid interactive efficient buildings. And those are broader than just state-owned buildings. It's state actions as well that they can take to enable demand flexibility in buildings within their jurisdiction. So my next slide, as promised, is lots and lots of resources that are available, and you can click on any of those links if you'd like to see the reports, or if you go to the next slide, there's my email address. You can reach out to me or Lisa about any questions that you have about any of the resources that I've mentioned. And I will stop there for any questions.
Thank you, Ms. Frick. We do have a few clarifying questions from the audience, and then we do have a few discussion questions. So the first question from the audience reads, sorry, the text is kind of small, but are the economic demand response type, so going back to one of your slides about demand response types, there's economic demand response types. So are the economic demand response type in MISO in retail utility programs, or are they participating directly in wholesale markets or through an aggregator?
I can't answer that question off the top of my head, but if you click on the link on the slide, and it's slide 23 that talks about the MISO DR resources, has the link to their independent market monitor report. It talks about all of the different DR resources, demand response resources, specifically the type 1 and 2. I didn't get the sense when I was reviewing the report that they were from utilities, but I would encourage whoever posed that question to dig into it from what the market monitor had to say.
This is Lisa. I'll just say that I'm looking at the report that Natalie sent me on this. So it does say for economic DR that it can satisfy the load serving entities resource adequacy requirements. That doesn't mean, you know, in terms of actual participation, whether the utilities are bidding or whether it's, you know, through aggregators solely, or even very large customers on their own.
Thank you so much, Lisa, for pulling that up. All right, the next clarifying question is, what were the results of the Entergy program that you showed?
I unfortunately do not have any evaluation, measurement, and verification from that Entergy program, but I will look and see if I can find any, and I will follow up with whoever that is. But I looked for some and ran out of time, so I'm sure there's some out there. I just didn't get a chance to look at them.
All right, here's more of a discussion question. Can you talk about pay-for-performance mechanism for energy efficiency and demand flexibility programs? How can pay-for-performance better align program compensation with DER value?
Yeah, sure. There's a variety of different states that are trying to do pay-for-performance and make sure that the utilities are able to, or the program administrators are generating savings when they're most valuable to the grid and potentially compensating those savings based on when the savings are being provided, depending on what the structure of the program is. So, you know, it's really about measuring what's happening and making sure that your energy savings or demand flexibility are occurring when you need them, and then potentially compensating them based on that in real time or in some kind of delayed format.
Thanks. So the next question is, what are some considerations for utility regulators to assess whether a utility has an appropriate balance between energy efficiency and demand response programs?
I think it depends on what your system needs are. As Chandler showed in his slides, and as we saw from the demand flexibility technology slides, there's lots of potential for efficiency and demand response to be combined together to produce peak demand reductions, or for efficiency on its own to produce peak demand reductions. So I think it's about first assessing what your system needs are, and then planning for your resources around that. I would like to think that there's always a place for energy efficiency in any portfolio, because it is a very low cost resource that, you know, once it's installed will most likely perform as it's supposed to for many years.
but you just have to take a look at what your system's needing and be responsive to that. It's also about making sure you have an appropriate mix to serve all of your customers as well. So making sure you're providing services to your moderate or low income customers, your industrials, your commercial, your residential, all across the board. So demand response doesn't necessarily always achieve that, but usually you can get a pretty big mix if you're doing energy efficiency programs that are serving everyone.
Thanks for that response. We have time for 2 more questions, but I just have one. So if anyone in the audience has any questions, please send them in. We have had demand response programs for a while. For example, direct load control of air conditioning and water heating programs. How is demand flexibility from grid interactive efficient buildings different?
Yeah, demand flexibility, I think, goes a little bit further than demand response. So it's not just about, a command and control approach where the utility is sending a signal to the building to perform. It's also about being able to increase load in response to generation that's on the grid that is either low cost or potentially low carbon. It's also about enabling customers to be responsive to different price signals as well. So it's just a little bit broader than what demand response is, which I feel like, as the commenter mentioned, is very much has been focused on direct load control of air conditioning and water heaters, and just kind of the utility telling that technology what to do. And so when you get into demand flexibility, you start to engage the customers more and start to think about how you can aggregate different buildings together, aggregate different technologies together, and create grid resources that probably have always been there, but just haven't been leveraged either individually or in an aggregated manner.
Well, thank you so much, Ms. Frick, for your time today and for your always contributing to our program. So we really appreciate your time with us. We're going to move to the break. We will let you go a few minutes early, but please take those few minutes to fill out the evaluations. Like I said, they are very helpful for us to shape the next set of programs. So they've really been used to justify today's program and future programs. So we really appreciate all the responses and your time with that. Again, today is day 3, and you do have a few questions on that evaluation about the program as a whole. So I'll let you out 2 minutes early, and we'll see you back at 2:15 Central Time, and that's 3:15 Eastern. See you then. All right, everybody, welcome back to our training. It's 3:15 Eastern, 2:15 Central Time, and I just dropped the links to the agenda and presentations and the evaluations for all 3 days. Please take a moment to fill all 3 out if you would not mind. We are getting things started with planning for energy storage and microgrids. I'm going to turn over to Lisa, and if you have any questions, just send them through the chat.
Thanks, Carrie. So we have a great presentation. It's 1 hour, covering in pretty good detail a lot of different topics related to storage and microgrids. First up, we have Jeremy Twitchell from Pacific Northwest National Lab, and then Andrew Mills from Berkeley Lab. So take it away, Jeremy.
All right, thank you, Lisa. So as Lisa mentioned, my name is Jeremy Twitchell, and I work at the Pacific Northwest National Laboratory. My main responsibility at the lab is on the Office of Electricity's Energy Storage Program in the equitable regulatory environment space. So the work that we do is trying to understand the regulatory barriers to energy storage and emerging practices, best practices for reducing or eliminating those barriers. Next slide, please. So I'll be giving you an overview of energy storage technologies today. So a little bit about different technologies, some of their relevant strengths and trade-offs. Then we'll talk a little bit about the services that energy storage can provide and some of the ways that we value those. Then we'll look at energy storage in regional markets, specifically in MISO in this case, and then a brief word about storage in microgrid applications. Next slide. And okay, one more, please. So the key takeaway here when we're talking about different types of energy storage is that energy storage comprises multiple technologies. And those technologies have different performance characteristics, different operational limitations. There are a lot of trade-offs. So there's 3 main types of energy storage. The first one here is mechanical. This is where we're taking electricity and we're storing it in the form of potential energy that we'll later use to generate more electricity. So in the case of pump storage hydro, we're using that electricity to pump water uphill, then later we release that water back through a generator to generate electricity. In compressed air energy storage, we're using electricity to compress air, and then later we're expanding and warming that air to power a generator. And in the case of flywheels, we're using electricity to wind them up one way and then releasing them to spin the other way and generate electricity. So the first 2 there, pump storage, hydro, compressed air energy storage, those are long duration technologies. You know, these can be configured, constructed to do 8 hours or more of energy discharge, especially in the case of pump storage hydro. Pump storage hydro has a better round trip efficiency. That's how much energy comes out relative to how much we put in. Very long cycle life. Both those technologies, though, not very flexible. You know, they can't respond to those momentary changes from one moment to the next in the grid, you know, things like frequency regulation. Flywheel is kind of the opposite of the other 2. Very short duration, 15 minutes top, incredibly flexible, good round trip efficiency, but because of that short duration, they're basically limited to those moment-to-moment applications like frequency regulation. Next slide, please. So electrochemical storage, here we're storing electricity in the form of chemical bonds that we're later releasing to recapture that electricity. Lithium-ion batteries, flow batteries, sodium batteries. You know, different characteristics, different trade-offs here. Lithium-ion obviously has a distinct advantage right now in terms of its commercialization with vehicle demand, creating supply chains, creating competition, creating lower costs. Some limitations, however, you know, safety concerns with fires, recycling challenges. Flow batteries, you lose some of that. You don't have the same fire risk. You do have high recyclability. One of the primary challenges we've seen with flow batteries, though, is that they are incredibly complex systems. There's pumps, there's machines, and engineering a device that can effectively and efficiently move these chemicals around for 15, 20 years is proven to be quite a challenge that we're still working our way through. Sodium batteries are kind of in between the other 2. Moderate durations, 4 to 6 hours, moderate round trip efficiency, moderate cycle life. The challenge with sodium is that you have to operate it at a very high temperature because the sodium exists in a molten state. which creates operational challenges and some safety risk. Next slide, please. And then finally, we have thermal energy storage, and this is where we're using electricity to heat or cool, air or some other medium for energy management or electricity production. So in the case of ice thermal storage, this is a rapidly growing technology, little different from the others in that we're not putting electricity back on the grid. We're taking electricity and then we're using it to offset future needs, by pre-cooling, by preheating, shifting that HVAC demand. Concentrating solar, long duration applications, 6 to 12 hours, really good round trip efficiency, fairly good life, some flexibility, not as much as you'd get from a battery, for example, but because it is ultimately powered by a generator, it does have some ramping and some flexibility characteristics. So if we could put up the poll question, please. Thank you. So question here is, we all know that battery energy storage has grown rapidly over the last few years, but from a grid perspective, from the amount of energy storage we have on the grid, how much of that is currently provided by battery technologies? Oh, this audience knows their stuff. That is correct. It's only about 4%. Next slide, please. Yeah, so we've got a little over 24 gigawatts of installed energy storage on the US grid at the moment. The vast majority of that, about 93%, comes in the form of pumped hydro storage. Batteries come next at about 4%, followed by thermal and compressed air. This is changing rapidly. The first time I made this slide about a year ago, batteries weren't even 2%. And based on what's currently in the pipeline to be commissioned by the end of the year, I expect we'll probably be somewhere between 5 and 6% by the end of the year. So rapidly growing. Of that battery technology that we have on the grid to the right there, lithium ion, the vast majority of it, about 88%, followed by lead acid, nickel, sodium, and then finally flow. Next slide, please. This is just a slide I threw in to point you to the report that's hyperlinked at the bottom down there. This is one that some of my colleagues did to look at various energy storage technologies and really understand how they differ operationally and what would their costs be if you put them all compare them all on an apples to apples basis. And I just wanted to call your attention to that first row under lithium ion, the capacity cost. That's just the battery itself, and you'll see in parentheses there that currently that's estimated to be about $189 per kilowatt hour. So you may have seen news articles, industry press lately talking about how lithium ion has broken that $200 per kilowatt hour barrier. Next slide, please. And there's 4 animations if you just want to go ahead and click through those and get those up there. Probably the easier way to do it. Thank you. To actually install a battery, to interconnect a battery to the grid, you have to have a lot more than just the battery itself. You need to have a power conversion system. Batteries operate on a direct current. So you need a power conversion system to move things from DC to AC and vice versa. You need balance of plant operations. You need all the controls, the switches. You need physical infrastructure. You need HVAC, especially if it's a lithium ion battery. You need those environmental controls. Construction and commissioning, you have to build that thing. And the point of all this, there's you see at the bottom, that all-in cost of the installed cost of a battery, best estimate right now is around $469 per kilowatt hour. So when you look at just those battery costs, which have been falling rapidly, it's important to remember that you're only talking about roughly 40% of the overall system costs are represented in that battery pack. Next slide. And next, one more. Thank you. So as everyone I'm sure is aware, energy storage can do a lot of things across the entire grid infrastructure. On the generation side, it can provide capacity for resource adequacy, it can provide energy, it can provide various ancillary services, regulation, frequency response, operational reserves, spinning, non-spinning reserves. As a transmission asset, it can provide thermal management, It can provide congestion relief, and it can also defer infrastructure in some instances. On the distribution system, voltage support, maintaining the voltage necessary for electricity to move through the system. Conservation voltage reduction, distributed generation integration, increasing hosting capacity, managing flows, and also infrastructure deferral again. And then finally, on the customer side, behind the meter, you've got rate management, demand charge reduction, power quality, and of course, resilience backup power. Next slide. Now, the values of all these services are highly locational. They depend on a lot of things. They depend on tariff structures. They depend on local grid characteristics. They depend on market rules, on utility needs. So this is from a report that some of my colleagues did a couple years ago, where they just looked, it's basically a gigantic literature survey, where they just looked at all the valuation of energy storage technologies that they could find at the time to understand what are the different values of these different services in different regions and different points of the grid. And so as you can see there is a lot of variation for these services. And so the key takeaway here is that when you're trying to really understand the value of an energy storage asset, you need modeling capabilities that can do two things. They need to be able to granularly understand those benefits that are available to the system. What is the benefit? What is the value of frequency regulation? What is the value of deferring a transmission line? And again, those are going to be highly locational. But then you also need the modeling capability to understand what are the operational characteristics of this device. Lithium ion in particular is very sensitive to how you use it. If you push it hard, if you discharge it quickly, you get lower round trip efficiency, you put more wear and tear on the battery. And so having a device that can do both those things, understand the economic value, but also the technical limitations, and then optimize on those two fronts is key to be able to identify the value of energy storage. Next slide, please. We've also been doing some work lately with this different paradigm of embedded energy storage. And if you think about electricity, it's unique among all the commodities that we use, in that its supply chain was developed without a storage component. So anything else you use, food, water, natural gas, it has that storage capability built into the supply chain. Things like warehouses, granaries, reservoirs, whatever they may be. And that embedded storage creates significant value to the system and to customers. It basically acts as a buffer between mismatches in supply and demand. It stabilizes prices. It protects customers. So one of the questions that we're starting to wrestle with is, now that we do have the ability to ubiquitously store energy storage across the grid, should we retrofit the grid with that capability? So, to date, we've been adding energy storage kind of, on the margins to kind of retrofit the grid with some degree of resilience, some degree of flexibility. But the idea here is, if we treated energy storage like just a grid asset, the same way we think about a transformer or a substation, then instead of trying to add on to make the grid flexible, we would just make the grid flexible. So there's a hyperlink there to the first report we did in this series. We're working on a couple others that you can see where to find them later on. Next slide, please. So conceptually, this is the type of value that embedded energy storage can provide to the grid. This is a very, very simple demonstration, down to the clip art that I used to put it together. But let's assume that we have a city that has an average demand of 1 million cubic feet of natural gas, but then it peaks to 1.5 million cubic feet. Then we have electric demand that's on average 100 megawatts, but then peaks to 125 megawatts. Well, if we compare how we design those two systems on the natural gas side, we can put a storage facility somewhere in the system so that upstream, we only need to size the system based on that average demand, just enough size to meet those average demands. Then that storage facility can store the excess, so that when we are in that peak condition, we only need to have the downstream portion sized to that 1.5 million cubic foot need. But if you contrast that with the electric side, we don't have that flexibility. If our peak demand is 125 megawatts, we have to design the entire system, generation, transmission, distribution, to meet that 125 megawatt demand. Even if we're only in that peak condition for a few hours of a year, the entire system has to be demanded to meet it. So the value is that where we have embedded storage on the natural gas system, we can more optimally design it. We can reduce system costs and have some efficiencies that we don't have available to us on the electric side now. Next slide. So it's an interesting idea, but there's a lot of questions that we're trying to work through here. On the regulatory side, we don't have standards that would justify this type of investment. There's nothing like this in our current reliability standards. There's no such thing as a resilience standard. So there's no clear entryway for this type of usage of energy storage. Planning processes, bulk power system planning process to regional transmission planning system or processes, they've historically been very slow to include new technologies. There's not really any clear requirements or mechanisms for new technologies to work their way into those processes. There's ownership questions. If this is embedded infrastructure, then it does have significant cybersecurity concerns, operational control needs, and who would own it? Is there even a mechanism by which third parties could participate in embedded energy storage? Compensation, how would you pay for this? If it's not participating in markets, is it just a regulated asset? And how do you justify? We all know this regulatory world very well. If there's not a justified need, then you can't make a case for that. And again, where there's no underlying standard that requires this type of usage, there's really no way to make that case. And then finally, metrics. How do you even measure this? How do you measure how effective it is? How do you measure its effect on the system and whether it's actually reducing system costs and improving operations? And then, on the valuation side, another issue we're starting to think about is, how do you quantify those grids, or excuse me, those benefits, and then how do you compensate the device for paying for them, or for providing them? Next slide, please. So moving on to storage in regional markets. So the Federal Energy Regulatory Commission, FERC, has two primary areas of authority over the electric grid. First is on the market side, regulating the market design and operations within the deregulated markets, which you can see there on the left. And then on the other side, the transmission side, FERC has authority over transmission system planning, operations, and rate making in all regions with interstate transmission. So even if there's not a deregulated market, like all these vertically integrated utilities out west that do operate interstate transmission systems are subject to FERC regulation on the transmission side. Important to point out, I went to graduate school in Texas, and I have professors who will kill me if I don't point out that Texas, because it does not have, the ERCOT region, because it does not have interstate connections, is not subject to FERC authority in either way. But the important note here is that FERC has used both of these lines of authority, the market side and the transmission side, in recent years to improve access for energy storage. Next slide, please. So on the market side, FERC issued Order 841 a couple years ago, and the crux of this order was FERC telling these deregulated markets that they had to reduce the barriers to energy storage participation in their markets. So FERC identified 7 specific criteria that the ISOs and RTOs had to meet. They had to create participation models for energy storage, make storage available or eligible to participate in all applicable markets, allowing it to do things like frequency response and potentially resource adequacy. And as they're doing this, they have to account for the unique operational characteristics of energy storage. Make sure that they've accounted for that and how the markets are designed, how products are designed, allowing asset owners to maintain their own state of charge, manage how they bid into those markets. And then also set a minimum size that's no greater than 100 kilowatts. Next slide. So focusing on MISO's implementation of Order 841. So MISO created this new resource type, the electric storage resource. They complied with FERC by saying that it can self-schedule, determine how and when it bids into markets. It has to be able to respond to a 5-minute dispatch signal from the ISO. So these have to be fast responding devices. The bids that storage devices have to submit are fairly substantial. There's 35 different things that they have to submit in their bids. Things like how much they're willing to pay to charge, how much they need in order to discharge, their ancillary service bids, startup bids, and then things like operational characteristics like ramp rate for the battery, discharge rate, the operational stuff. And then if a storage device is not selected in the day-ahead market process, then it is eligible to participate in the reliability assessment commitments where applicable. Next slide, please. So FERC accepted MISO's initial filing, but did request an additional compliance filing to clarify a few things. The big one with MISO was, so FERC had said that any resource, that there was a minimal size for resources that could not be greater than 100 or smaller than 100 kilowatts, greater than 100 kilowatts. And so MISO did that, but MISO also put a cap on the number of those smaller facilities that can participate in the market. And FERC denied that, told them to remove that cap. That was the main issue that came out of that first filing. A couple other details you can see there. The compliance filing was accepted, but FERC actually requested another compliance filing to add some additional clarity about how MISO would handle metering and compensation for distribution connected energy storage that's also providing retail services. And so that second compliance filing is pending. Next slide. So on the transmission side of the house, oh, sorry, there was a poll there. So the idea here is trying to understand, what do you see the primary value of energy storage being in your state? Are you looking at it for renewables integration, for providing ancillary services on the grid, peak shaving, resilience? So if you could please let us know. Wow, interesting. Lots of interest in renewables integration. Okay. Great, thank you. So the transmission side of the house, FERC, well, this was prompted by a couple cases that FERC did back in 2008 and 2010. In both these cases, there was a pump storage hydro developer that came to FERC and said, hey, we think that we should be a transmission asset, and we would like a declaratory order to that effect. FERC said yes to one and no to the other. And if you dive into those proceedings, there's a whole lot of nuance as to why FERC came to those differing conclusions. But over the years, as these cases were cited in other proceedings, it became clear to FERC that a lot of that nuance had not been perceived. So they put out this policy statement in 2017 to clarify their view on this. And they said energy storage can be a dual use asset. And that's where it's a regulated transmission asset that also provides competitive market services, and that it can earn revenue from both operations, subject to these principles. It can't double recover its costs. It can't have unfair access to markets. There can't be any adverse impacts on the bidding process. And the ISO's independence must not be compromised. So basically, FERC said when the asset is operating in transmission mode, the ISO controls it. When it's operating in competitive mode, when it's operating in generation mode, operations revert to the owner, and the owner is responsible for putting in those bids and meeting its obligations. Policy statement is not binding, doesn't require anyone to do anything. CAISO, the California ISO, and MISO were actually the only two regional markets that initiated proceedings in response to this policy statement. Next slide, please. And it's really interesting. So MISO's proceeding was initiated about a little over a couple years ago, and it identified the policy statement as one of its driving factors. Interesting to note that CAISO and MISO took completely divergent approaches to this. CAISO focused on enabling dual use energy storage, and they set aside that question of how do we identify storage in the transmission planning process. CAISO said that's not what we're doing here. We're interested in this dual use question. MISO went the opposite route. They ultimately decided, okay, we're going to set aside the dual use question. We're going to focus on storage as a transmission asset. So MISO's storage is a transmission asset only. I put that in wrong. I just realized that transmission only asset, SATOA, clarified that where storage is selected through a transmission planning process, it's only a transmission asset. It's not eligible for market participation. If it wants to provide market services, it should come in as a generation asset. But what SATOA did, what this filing did that has not been done in most regions though, is clarify the process by which energy storage will be considered in regional transmission plans, and adding some additional clarity and transparency for how those analyses will be performed and how those decisions will be made. Next slide, please. So, quick example of how storage can be provided, how storage can serve as a transmission asset from MISO. So the 2019 transmission expansion plan was actually the first MISO plan to identify energy storage as a transmission asset. This is actually the second time it had happened anywhere. CAISO did it the year before in 2018. So near Waupaca, I'm probably saying that wrong, sorry, Wisconsin, they identified a contingency scenario, an N-1 scenario, where if a transmission line near Waupaca went out of service, the entire region would be cut off. And so they looked at their options, and they could install an additional circuit, add some redundancy in the area for $13.1 million, or they could add an energy storage system coupled with some line segmentation, some capacitors on the line, that would achieve the same outcome, that would maintain the Waupaca region in the event of that line outage at $12.2 million. So as the least cost option, it was selected. The expected in-service date is in December 2021. So important to remember that this is a transmission asset only. It will be recovered through MISO's FERC-approved transmission system rates, and it will not participate in energy markets. Next slide. So moving quickly to storage and microgrids. Thank you. So the paradigm that we've been operating under for resilience, for backup power, is generator based. If I'm a facility, or if I'm a homeowner that wants to have backup power, I go out and I buy a generator. That generator provides me energy and capacity, but I don't have very many options. I probably don't have any options to participate in the grid, to provide cell services back to the grid. My energy and capacity from my generator isn't particularly cost effective. It's not particularly easy to put back on the grid. So I absorb all those costs as the homeowner, as a facility owner. I have to buy the device, I have to buy and store the fuel, I have to do the maintenance. And so that adds up, that's expensive. And so traditionally, resilience has largely been limited to facilities where it's mission critical, hospitals, military bases, sensitive manufacturing facilities, places like that. But now with energy storage, we have this new paradigm where we can take that storage device, and then we can take that generator, we can take our distributed generation, distributed solar, distributed wind, and we can use the storage device to shape all that generation. So now we're not just providing capacity and energy, we can also provide regulation, arbitrage, operating reserves, and now we can provide valuable grid services. So we have increased opportunities to participate in the grid. And by doing so, by providing those services, we can earn offsetting revenue that reduces the cost of the system, thereby making these resilience projects, these resilience investments cost effective to larger groups. So now you're starting to see resilience take off at places like schools, community centers, dispatch centers, police departments, much bigger group investing in that now. Next slide. So don't need to speak to these, just wanted to leave a few questions, a few examples of the type of questions that states that policymakers and regulators can be asking in these processes as they're participating in them, as you're reviewing utility filings, participating in regional proceedings, things like that. Next slide. And then, just wanted to leave you with a few resources for additional information about energy storage. That first group up there, you can see a few reports talking about energy storage, particularly in microgrid applications. That fourth one down, the planning considerations for energy storage and resilience applications. That's that graphic a couple slides ago about increased opportunities for resilience because of energy storage comes from that report. And then we walked through some of the planning considerations, what it would look like from a planning perspective to consider some of these applications for energy storage and resilience. And then at the bottom there, you can see links to a few laboratory websites and other resources. And I know we don't have a lot of time today, but I'm happy to take any questions anyone might have. My contact information's there, and appreciate the opportunity.
Thanks, Jeremy. You actually did really well for time. So Andrew, you can take more time as you need it. We actually have, I think I misspoke earlier, we actually have a total of 75 minutes for the session. And so, feel free to take more time. We're looking for questions in the chat box. If you have any questions for Jeremy or Andrew, we'll take them following Andrew's presentation. Thanks, Andrew.
Okay, great, thanks. So good afternoon. I am Andrew Mills, a research scientist in the Electricity Markets and Policy Department at the Lawrence Berkeley National Laboratory. I'm going to talk about potential roles for storage in integrating variable renewable resources and also the emerging commercial interest in hybrid renewable plants. The goal of this is to share some of the insights from our research that can inform discussions about use cases for storage and important factors to consider. So I'll first talk about integration, and this section will primarily focus on the challenges of integrating variable renewable resources into the grid. Integration challenges include the variability of resources and also their contribution to resource adequacy. Variability is associated with the changes in supply within the operating hour or over multi-hour events. Uncertainty, on the other hand, is due to forecast errors, maybe in the day ahead or also closer into real time. A consequence of the variability and uncertainty is that the actual supply of generation will deviate from what was originally scheduled. And covering these deviations can require flexible resources to quickly respond, or it might require system operators to hold resources in reserve to cover those deviations. Actually, can you go back a couple slides? There you go. Yeah, go ahead and keep it on this one. Thanks. The fact that generation from variable resources is not aligned with times of greatest system needs leads to a lower contribution towards meeting resource adequacy requirements. So in many regions, the contribution of wind to resource adequacy might be only something like 25% or less of its nameplate capacity. The contribution of solar is higher often, but still it might be somewhere in the range of about 50% of its nameplate capacity. And then we see experience with high penetrations of solar in California that shows how the timing of greatest risk of outages can actually start to shift from the hot sort of summer afternoons into the early evening after the sun sets. So I'll talk about both of these two issues here and then describe some of the research that we're doing on how storage might be used to address these challenges. Next slide. One thing to keep in mind is that variability and uncertainty are inherently part of power systems due to the varying load. And so variable renewables increase this variability and uncertainty, and managing that can impose additional costs. Go ahead and go to the next slide. Over the past 2 decades, numerous studies have been conducted across the US and internationally to understand these integration costs of wind and solar. The resulting integration costs that you see from these studies differ across the studies for many different reasons, including differences in the mix of resources in the region. So that might include things like how flexible is the generation that's in that region. It also can differ because of whether these costs arise for a utility that's its own balancing authority, or if that utility is part of a larger coordinated regional system. And then we just see differences in how the studies themselves define and calculate these integration costs. And one of the places that we see these costs often discussed is in the context of integrated resource planning. And the reason is that standard grid planning models may not capture the full extent of this variability and uncertainty of renewables. And so to address this gap, detailed studies are often used to estimate the costs of these particular aspects that are not directly captured in the planning models. And I'll show some of those results from studies on the next slide here. Go ahead and flip to the next slide, please. Yeah, there you go, thanks. So most wind integration studies find that the costs associated with managing this additional variability and uncertainty of wind are below about $5 per megawatt hour of wind energy. There's a few exceptions to this, and that tends to happen when you have smaller utilities that are their own balancing authority, and that's more common in the Western US. The other thing that's interesting to note about this is that you don't see that these costs necessarily dramatically increase with penetration levels, that a number of studies that have done multiple penetration levels don't necessarily see a real steep rise, although you've seen that in some particular earlier studies. Next slide, please. There's a smaller number of studies that have estimated these integration costs for solar. And one thing that we see is that they tend to show a general range of costs that are somewhat in the same ballpark of what we've seen for wind. The particular study here in dark blue that's marked APS Argonne 2013, that was based off of a study that involved researchers from the Argonne National Lab, Berkeley Lab, and then the National Renewable Energy Lab. So I'll talk just a little bit more about the results of that particular study in the next slide. And again, one of the things that sort of is raised by this is why are those costs not considerably higher than you might expect, given that variability and uncertainty. Next slide, thanks. And one of the things that's clear is that if you look at individual power plants, you can see dramatic variability due to passing clouds, and that this cloud cover can oftentimes be hard to predict. So the red lines in these charts here show the solar output from 32 different simulated PV plants on a relatively clear day with the parts that are on the left, and then a relatively like a partly cloudy day on the right. And if you look at some of these individual sites, you can see that production from these plants can just drop off in minutes at that individual site. So what we did was the study itself focused instead on strategies and costs for managing the solar at the aggregated level of the balancing authority. So we took the output from all of those same plants and saw that when we aggregated it, that it could become much more smooth across all of those 32 plants in the entire utility footprint. And in particular, that rapid drop-off in production that we could see at a single plant didn't really appear in the aggregate profile, and that's what's shown in the black lines, even on that partly cloudy day. So as a result of this, when we went and ran the study at what sort of additional incremental reserves might be required to manage this variability and uncertainty, we saw that those costs again would come in from somewhere below that $5 a megawatt hour range that we've seen from a number of studies. Next slide, please. So alternatively, we've also evaluated an often discussed strategy of instead trying to smooth the PV ramps directly at that individual plant level using storage. So here you can see how we simulated the operation of a battery that's used to limit these ramps from an individual PV plant. And on a partly cloudy day, that's on the right-hand side there, you can see that the battery has to be rapidly charged and discharged in order to limit the ramp that would come from the PV and battery system. And in this case, we designed the battery to try to limit that ramp to about 5% of the PV capacity per minute. And then the battery size itself, the capacity of the battery was sized similar to the PV plant. So in this case, it was like a 75 kilowatt PV plant. And so we also had similarly like a 75 kilowatt battery. But the amount of energy that that battery needed to store was relatively small. So at full power, that battery would be completely discharged in 15 minutes. And that was sufficient to be able to cover all of these conditions, including this partly cloudy day where you saw a lot of rapid output changes from the passing clouds. Next slide, please. So we took that battery dispatch profile and the characteristics of that battery in terms of the dimensioning of it and sort of ran an analysis where we would look at different ramp limits that we'd be looking at and use this on different PV profiles. We put that into NREL's SAM model, which has the ability to reflect some of the battery operations and some of the degradation that might occur as you start to cycle batteries. And then we use that to then calculate what the total system costs would be, how often that battery would be degraded and then need to be replaced and so on. And really that replacement comes from that cycling of the battery, that it can be costly to really cycle that battery very quickly. And again, in this case, we're talking about something like a lithium ion battery providing this service. I think it was really helpful to hear Jeremy's presentation before this because the degradation that you see for providing the same service here will really depend on what sort of technology you're using. And we're focusing on lithium ion batteries, which will degrade under that cycling. Next slide. So what we did was we then used this model to then estimate the incremental increase in the cost of a PV system due to this additional battery equipment cost that you would add on to that PV plant to provide this ramp control. And we looked at this for different levels of stringency of that maximum ramp rate. So the more stringent you were, the more you wanted to really reduce those ramps and smooth out the output of that PV plant, the more you'd have to add additional battery equipment. In particular, you were increasing the duration of that battery to provide that ramp control. what that meant was that in order to meet that higher ramp rate limit, or sort of more stringent ramp rate limit, you would increase the initial cost of this. And if we look at what the cost would be per megawatt hour of solar generation, we estimated that this using the battery to do the smoothing function would range from about $10 per megawatt hour to $40 a megawatt hour of additional costs, depending on the degree of smoothing that you're requiring. One other interesting finding from this chart that you can see here is that the costs were higher when we looked at this for just this small 75 kilowatt PV system using PV data from the city of Tallahassee. So that's what's shown in the orange bars. And that's relative to the blue bars, which are a 12.5 megawatt PV system that was located in Jacksonville. And presumably the lower cost that we see here for that larger plant happens because there was less need for the batteries to be rapidly cycled to provide that smoothing, because even within that single power plant, there was already some smoothing that happens. There's already some effective aggregation that smooths out the output of those cloud-induced fluctuations. And so the resulting sort of changes in output that had to be provided by the storage asset were less for that larger plant, for that larger footprint plant. And so therefore we cycled the battery less, we ended up needing to replace that battery less often, and then therefore the costs of doing that were somewhat less. So the main takeaway from this analysis that we saw was just to say, if you compare this cost here to what we've seen from some of those integration costs, is that although you can take storage and try to smooth the output of an individual plant, it can be sometimes easier and more cost-effective to manage the aggregate variability at the balancing authority level first. And once you've sort of aggregated that up, then you take that residual amount that's left, and that's what you would use flexible resources to try to address. And that might come from storage, might come from other resources that you have on the grid. So now go ahead and go to the next slide. I'll now turn to the other issue related to integration, which is this lower contribution of variable renewables to resource adequacy targets. Again, I'll just sort of start off by introducing the concept and then discuss some findings from research on using storage to contribute to resource adequacy. Really, one of the things that we've seen in a lot of studies is that the contribution of renewable resources to resource adequacy targets depends on the production during times when there's the highest risk of insufficient generation to meet demand. And with historical low penetration levels of wind and solar, these periods of highest risk of outages, that was often occurring in the mid-afternoon peak peak summer days. And so this is showing some analysis from MISO. And so if you were to look at historic levels of risk, that would tend to be kind of concentrated in this time around 3 o'clock in the afternoon. And then the charts on the left show that the renewable production that was happening at these lower penetration levels would be somewhat high for solar penetration. That's in the yellow lines. You'd see that you'd not do too bad of lining up with those times of high system risk at low penetration levels. And then wind was somewhat worse in that it tended to produce less during the middle of a summer day than it would do at nighttime. So then if you were to take that low penetration level, look at the production of solar during those times of high risk, and then use that to calculate what the contribution of solar would be to meeting those resource adequacy targets, which is what's shown on the right, you would find a capacity credit of solar that might be as high as about 60% of its nameplate capacity. So it means if you had 100 megawatts of PV, you might count 60 megawatts of that towards helping you to meet your resource adequacy targets. While wind, under those same conditions, would only get something like a 20% capacity credit. And then the method that's being used here in particular, and why it's being labeled ELCC, is that they're using something called, they're using a probabilistic model of risk of outages and calculating something that's called the effective load carrying capability. So this is sort of somewhat seen as sort of the gold standard of how you might calculate the contribution of different resources to resource adequacy. One of the important things that a model like this can capture is that as you start to increase the share of renewables, that time of the period of when you'd have the highest risk can start to shift. And in particular, it shifts away from those traditional times in the afternoon and increasingly goes towards early evening after the sun has set. What this does is that means that now the timing of solar production, for example, in the early evening is going down towards zero. And so the incremental capacity credit of additional storage at that point can start to decline very rapidly. And so you can see as you add more and more solar, that capacity credit would decline from that high of 60% to dropping below even the level that we saw of wind at low penetration levels. Now wind, because it's not necessarily well correlated with that peak in the first place, and it's sort of distributed a little bit more over all hours of the year, doesn't tend to push the peaks in those ways as much. And so in some cases, you could even see that as you push that peak towards the evening, that might actually increase the contribution that you're getting from wind to some degree. So there might be some sort of synergies that occur with those two. But aside from that, now what we're going to talk about in the next slide is to then start to see how could storage play a role in helping to increase those resource adequacy contributions of renewable resources. One of the challenges that we faced with starting to look into this literature and the methods for doing that is to answer the question of how would you actually dispatch that storage if its primary role is related to that resource adequacy function. And so what we did in our research is we developed a simple and fast algorithm that could be used to dispatch storage such that it would maximize its capacity credit. This particular method builds on an approximation of the capacity credit that NREL uses in some of their resource planning models, such as the REEDS model also. And what it does is that it really focuses in on how well the resource is able to decrease the peak net load periods. In this case, it's in the top 100 peak net load hours. And so our algorithm is basically going to take storage and try to dispatch it in a way that would maximize its production during those peak net load hours, accounting for any shifts that might occur as we add more storage or as we add more solar and so on. So we're gonna track what's happening with that and make sure that we're always dispatching the storage in order to maximize its capacity credit under those conditions. Next slide. So we took that approach that we developed, which was a fairly simple and fast tool that we could use that didn't require anything in terms of proprietary data. And we went and validated that by comparing it to an approach where a utility who had access to state-of-the-art models and then also the data that would be required to run one of those models based off of their own utility system. And we effectively benchmarked our method against theirs by using the exact same net load data and solar production data and so on, and then use that to calculate the capacity credit of storage and benchmark that against the dashed lines here, which are the results directly from that utility using their own tools and methods. And one of the things that you see that's interesting is that both of these methods show that as you increase the amount of storage that's being deployed in the system, that the capacity of storage can also start to decrease. And this can happen because as you add more and more storage, the remaining peak that has to be reduced by that next increment of storage starts to get wider and wider. So you start off by sort of reducing those top kind of narrow peaks, but then as you've done that, the remaining peak gets wider and wider. And so that requires longer and longer duration storage. Or if you're just having 4 hours of duration, the capacity credit of that 4-hour duration storage starts to decrease. The other things that both of these models showed was that if you have a higher share of solar in your power system, then one of the things that high amounts of solar can tend to do is that it narrows those net load peaks. And the previous slide also showed that to some degree with the data from MISO. If you have narrower net load peaks, then those are somewhat easier to meet with that 4-hour duration storage. And therefore, the capacity credit of storage with high solar, which was shown by the red lines, is actually going to be somewhat higher than the capacity credit of storage in the exact same system with lower penetrations of solar, which are shown by the blue lines. And again, the main purpose of this was to just validate our method that we had used. And then in the next slide, what we'll do is we'll take that same approach and we'll start to evaluate the capacity credit of different configurations of solar and storage. Next slide, please. So if you had a solar and storage system and you wanted to combine those two together, you have a different configuration options that you could evaluate. So we start off by basically just having these completely independent. We have a PV plant and a storage plant. They share no equipment. They don't have any sort of shared infrastructure, so there's no point of interconnection limit or anything like that that constrains their output. And also we allow that storage asset to go ahead and charge and discharge from the grid as needed. And so that would be our sort of our baseline configuration. And then if we brought those two together into the same plant, we have a couple of choices that we can also make and how we do that. So one option is that we can connect those PV and storage both together on the DC side, which means that we're sharing an inverter, but then still allow that storage to charge or discharge from the grid. So that's what we call a loosely coupled configuration. So they're sharing some inverter, but the storage is charging from the grid if it needs to. And then in the tightly coupled configuration, we again connect the battery and the PV plants on the DC side and share that equipment. But then we only allow the storage to charge from the PV plant now. So this is the tightly coupled because we're restricting it to only charge from storage. And so our questions with this were just to go through and see how these different choices about configurations would impact the capacity credit of this asset. Next slide, please. And what we found, one of the things you see here is that the capacity credit of storage really depends on its duration. So the x-axis here is showing different durations of that same storage asset, and the blue line is the capacity credit of storage by itself. And so as you increase the duration of that, you're adding more and more energy to that system, the capacity credit will go up and start to sort of plateau after you've hit about 4 or 5 hours of duration. If we have an independent system, then we just effectively take that storage capacity credit and we add on top of it the solar capacity credit. And you can see what happens there in the red line when we have those independent assets. And then what you can see is that if you start to bring these things together and you have any sort of shared infrastructure, like a shared inverter, or you have a shared point of interconnection limit, like you do in these green and purple lines, then one of the things that can happen is that you can start to run into the situation where your solar would be discharging at the same time as your storage potentially, and effectively cap what the total capacity credit might be of that solar and storage asset. And so that's one thing that's important to keep in mind as you bring these together, is that any sort of limitations like that, it can effectively impose a constraint that might limit the flexibility of the storage that you're able to get out of it. And so you want to be cognizant of that and sort of design that system accordingly. The other thing that was interesting, if we focus, if you stay on that same slide, if you focus on the results on the chart on the right, this is what we found with the utility in Jacksonville, where they tend to have both high load in the summer, but then also with very narrow high winter peak events that happen when you have a storm that comes through and there's a lot of electrical heating demand that would suddenly spike up during that time. And so one of the things that we see here is that in that case, if we are restricting the storage to only charge from solar, in that tightly coupled case in the green line, we could end up in situations where during these winter cold weather events, the solar would be insufficient to charge the storage, and we'd actually end up lowering our capacity credit to some degree. These are not large effects that we're seeing necessarily, but again, just something that's important to keep in mind and to think about that when you're designing these systems and thinking about whether or not you want to be restricting the way that the battery is operated and where it can charge and discharge from. And just overall, the key message from this is that storage can contribute to resource adequacy, but the specific contribution of it is really going to depend on these configuration options. Next slide. So for the last part of this presentation, I'm going to turn now and sort of widen the lens a little bit to talk about the commercial activity that we've been seeing for these combined renewable energy and storage plants, and really start to talk a little bit about these broader motivations for deployment. Next slide. And one of the things you can see is that the overall motivations for hybrid plants do extend well beyond just some of the narrow issues that we've talked about so far. One of the important motivators for some of these hybrid plants is the investment tax credit. And so the federal policy is playing a role here. And what happens is that the storage capital costs can be reduced by this investment tax credit as long as the storage is being charged from a renewable resource. If you had that same standalone storage asset and it wasn't being charged from a renewable resource, it would not be eligible for that same incentive. And there are some nuances to that. It's basically that the minimum amount that you have to be charged is 75%, and then you prorate sort of the investment tax credit for anything below 100% charging of this from the renewable plant. And if you're fully charging, you get that full 30% reduction in your capital costs. But aside from these policy considerations, there are some true cost reductions that can come from things like shared permitting costs, shared interconnection costs, and also perhaps sort of the ability to accelerate your interconnection process by having a single process to go through rather than multiple different assets. And then there's other equipment, again, that you might be able to share between these equipment and reduce, between these assets and reduce their costs. The other thing that's interesting to think about is that when you do have solar and storage connecting on that DC side, that there's a potential that you have some energy that would otherwise be clipped from those PV panels because the panel might be oversized relative to the inverter. And if you place storage on that DC side, you might be able to capture some of that clipped energy and then use that later. So that can be another motivator for some of these plants. On the other hand, there might be some opportunities that you might forego. So if you're taking that storage asset and you're deciding to site it with a renewable generator, there might be other places within the system where you might be closer to loads or where you could potentially defer some of these transmission investments and so on, that you'd sort of like lose out on that opportunity potentially. So it's important to kind of think about, is there any opportunity cost associated with bringing that storage into the location of the renewable plant? And then again, we've talked a little bit about how there might be some operational flexibility that's limited because of some constraints that you would apply on that storage when it's in a hybrid function versus if it was just independent on the grid. And then finally, there is some regulatory uncertainty. In particular, there are some market rules for interconnecting hybrid resources and for participation models in wholesale markets that they continue to evolve, and there's a lot of really interesting discussions happening on those that are going to be important for making the business case for some of these. Next slide. Okay, so now we'll take one quick poll, which is just to ask a question of which model for energy storage deployment is or is likely to be the most used in your state. Option A is as a standalone front of the meter asset. Option B is as a behind the meter asset. And option C is a hybrid with a co-located generator. Okay, now there we go, show the results. Okay, and so there's a lot of interest in these hybrid co-located with generators in these results, and also a lot of interest in the behind the meter asset and a little bit less in the standalone configuration. So your poll results, go ahead and go to the next slide, please, are in line with what we're seeing with commercial interest, and that commercial interest in these hybrid plants is really growing. And I'll go through in the next couple slides some data that shows that growing interest based on shifting activity in interconnection queues. And one of the things you see is that interconnection queues across the country are dominated by wind and solar. And there's also a growing interest in storage in these interconnection queues. And that storage will be in some of these standalone, but also in the hybrid options with wind and solar plants. The hybrid portion of this is shown in the hatched bars there, where that's the quantity that has storage paired with it. Now, with these interconnection queues, it's important to keep in mind not all of this is going to be built, but what it does is give us sort of a sense of the activity that's in the development pipeline and some of the trends that are taking place in the industry. Next slide. The bulk of this hybrid activity is happening with solar and storage, and most of that is happening in the Western United States, where we do see increasing levels of solar penetration. And for solar, if you look at what's the sizing of these, the batteries tend to be sized about 66% of the nameplate capacity of the solar plant. So they're fairly large batteries relative to the solar plant. Whereas on the other hand, for wind plants, those batteries are sized at a smaller size at only about 27% of the wind nameplate capacity. Next slide. Another interesting finding is that about 2/3 of the solar and about half of the wind in the California ISO queue now has storage with it. And if you look at just what came into the queue in 2019, it's even higher. It's like something like 95% of what was added in just 2019 had storage with the solar plants. If we were to go across the country to other locations, you see growing interest in these hybrids also. MISO, for example, about 17% of the proposed solar capacity would be also hybridizing with storage, whereas only about 2% of the wind in MISO would be adding storage with it. And that might, again, reflect some of these issues associated with the investment tax credit, perhaps, or just some of these synergies that we see with resource adequacy and solar. So next slide. In these last few slides, I'm just going to go ahead and summarize some of the limited cost data that we have that we've collected for a small subset of these projects. And these are projects that have signed PPAs. And then we also did some preliminary modeling of the value of hybrids using historical market prices. Next slide. If we look at this cost data for, again, a subset of the projects that we saw before, one clear trend is that the cost of solar and storage hybrids are really declining. The projects in the Southwest that have signed agreements, some of them have been signed at as low as sort of the $20 to $30 per megawatt hour range. If we were to look at Hawaii, we see projects that are quite a bit more expensive than this, but they are following sort of a similar downward trend in the costs. Next slide. So for a small subset of these projects that we have cost information, we've also been able to tease out just what the additional incremental cost is of the battery. And one of the things you see is that this cost adder of adding storage to the PV system increases as that battery gets larger and larger relative to the PV plant capacity. If we were to look at a 4-hour duration battery, again, 4-hour duration gets you sort of close to that 100% capacity credit. And if that's sized to about 50% of the PV nameplate capacity, that would increase the costs of a PV plant by about $10 per megawatt hour based off of what we've seen from these signed PPA prices. Next slide. So we were interested in looking at the other side of this and thinking about what's the additional market value you might get from adding this storage. So here we're going to use historical market prices to estimate the additional value of adding storage to a solar plant or adding storage to a wind plant. Now, rather than dedicating this battery to doing smoothing of the variable renewable generator or doing something where we're just focusing on resource adequacy, in this analysis, we're dispatching this battery to maximize the revenue of that battery or that battery and hybrid system. And we're subjecting it to constraints that might be things about the limited point of interconnection, or we might restrict the battery to just charge from the renewable generator. And what we find in these results here is that the addition of a battery can increase the value of a wind or solar plant in California significantly more than what we saw in Texas. And the reasons for this increase in value in California in particular come from, in part, this increase in capacity value. So again, a 4-hour storage gets 100% capacity credit in California, and therefore is able to qualify for some of these resource adequacy contracts. And so we valued it at the price of those contracts. We also see that there's a lot of volatility in California prices during this period of 2016 to 2018. And part of that is driven by the fact that we have sort of lower prices during the time we might call the belly of the duck, and then increasing prices at the times of the end of the ramp when we have the high net loads sort of at the neck of the duck. And so that increased volatility would also then increase the value of storage that can maximize its revenue by dispatching against those prices. So if we compare these estimates of the increase in value of adding storage to the previous estimate that we had of the increase in cost of about $10 per megawatt hour for a similar configuration, then in California, that battery would start to look fairly attractive. But in Texas, it would be less so because of that lower volatility in prices during that particular historical year. Next slide. So we can look at that exact same situation just from somewhat of a different lens here. And so this is, again, the same data just presented in a different way, which is, in this case, we've thought about this idea that you might have a standalone renewable generator, but you could also have a standalone storage asset that's out there. And so we want to compare the value of those two standalone assets, where now in the standalone storage, you're just dispatching it to maximize its revenue, whatever, based on the grid prices. And then compare that to the hybrid plant, where we're now bringing those together and potentially subjecting them to some constraints. And that, again, could be things like the point of interconnection limit. We might be restricting the battery to only charge from the solar or wind in this case. You can see that there's a slight reduction that you would see in the value because of that, but it wasn't dramatic. It was somewhere on the order of about 7 to 11% of the value would be reduced by hybridizing. And so what you want to do is, if there are some of those value reductions, you want to compare that to those cost synergies we talked about from things like the investment tax credit or reducing interconnection costs, other factors like that that might be on the plus side for doing that. Okay, next slide. So I'll just wrap it up here. I just have a few questions that I'll run through that states might ask utilities, and this just sort of summarizes some of what I've talked about today. But so as you're bringing storage and hybrids into these planning discussions, you might ask questions like, how do you take advantage of this geographic diversity to manage challenges with variability and uncertainty? And we saw that a variability at a plant level can be much greater than the variability when you kind of aggregate over the footprint of a utility. And managing this aggregate output requires fewer reserves and it can be less costly. Another question is how much storage is needed to manage the aggregate variability and uncertainty compared to managing at each individual plant. And so if you're using that storage to manage variability and uncertainty, less storage may be needed, and the storage would be cycled less often if you're doing that sort of at that aggregate ramp level, rather than trying, again, to kind of do that at the individual plant. Another question to ask is how your resource adequacy assessments account for any potential changes in the contribution of resources with increased deployment. We've seen that particularly for solar, the resource adequacy contribution can decline with increasing penetration. And these capacity accreditation methods that are being used in practice should really try to account for this decline and the potential implications that we might see from this shifting period of high risk. Again, sort of a trend towards from summer afternoons into the early evenings. And then another question would be, how do the costs and benefits of hybrid configurations compare to the standalone configurations? And just again, whenever you're evaluating these hybrids, it might be helpful to just sort of think about this, the attractiveness of that asset relative to what it would look like if you were to do this with a standalone configuration. And is there any sort of opportunity cost or are there some synergies? So that's another question you might ask is, what are some of these potential cost or value synergies of hybrids that you're accounting for in your planning and procurement? And again, some of these things might come from reducing costs through the ITC, might come from reducing costs by sharing equipment or interconnection, and which of these are sort of being included or drive some of the evaluation. And then finally, one other question is that if you do allow or prevent grid charging for hybrids, that might have some consequences for it. It might have consequences on the value side, but it also might affect things with eligibility for state policies. And so I think that's just something to be thinking about, is that if you do allow this storage to charge sometimes from the grid, that can potentially increase its value and increase its flexibility, but that might have some impacts on eligibility for renewable portfolio standards or clean energy standards. It's important to consider. Okay, and then I think the last slides are just some summary resources if you're interested in following up on some of those documents. Thanks. I'll look forward to the questions.
Thanks, Andrew, and thanks, Jeremy. So we have a few questions that we have time for before our final session on electric vehicles and managed charging. So Jeremy, two questions, if you can answer quickly, I'll ask them in turn. First, how are the end of useful life and recycling of storage assets being considered? You know, are they included in the all-in cost?
Great question. They generally have not been, because we as an industry, we as a nation are still behind the curve when it comes to recycling battery technologies. We don't yet have a commercialized way of doing that. The Department of Energy is investing heavily in that. They set up the first battery recycling research center at Argonne National Laboratory last year. They're also supporting a prize for anyone who can demonstrate cost-effective means of recycling battery storage technologies. And these prizes actually have a very good track record. The first commercial LED light bulb that we had actually came from a similar prize type competition. So lots of work being done, but not much to report right now.
Thanks. And one more question for you. On one of your slides, you talked about a Wisconsin project that was storage as a transmission only asset. And I think you mentioned that it was planned to be in place for 40 years. And we have questions about that. I mean, can it have a 40-year life? How are we looking at these, related to the first question also, how do we deal with these significant end of life issues and environmental impacts in the long run, both for storage and renewable resources?
Yeah, so there's a couple ways to look at it. So when we're talking about the useful life of an energy storage system, of a battery system, we're talking about in terms of cycle life. So the cycle life for a lithium ion battery right now is about 3,500 cycles. So if you're using it on a daily basis, daily cycling, you'll get about 10 years out of it. In a situation like this, where it's a transmission only asset and it's only being used in contingency situations, most years you probably won't even touch it. It's only going to be used in unique situations. So something like that where it's just sitting most of the time and it's only being charged and discharged occasionally for maintenance, it's going to have a much longer life. 15, 20 years is entirely reasonable. And when there's two ways to look at this, you can look at this in terms of deferring the transmission investment and looking at that time value of money by deferring that investment out 15, 20 years, or you can look at it in terms of a total replacement where you're building in those back end costs to re-up that capacity, to replace the battery and get that full 40 years. I don't know off the top of my head, I can't remember which they were doing in this Waupaca situation, but there are two options for how you can treat that.
All right, now that's really helpful. Andrew, I have a couple questions here for you. One is, from the perspective, you talked in part about from the perspective of a project developer or a project owner, what are their incentives with respect to hybrid projects versus standalone? But if we flip that and we're looking at the perspective of the electricity system, is there any more value really with respect to a combined solar plus storage plant versus the utility or RTO using its portfolio of resources throughout the system to integrate solar? So really from that electricity system perspective.
Yeah, it's a great question. I do think that one of the things that we have seen is that there are benefits to those portfolio options, and that can be a really strong. It's worked over the 100 years of doing this in the power system. That you tend to build out the transmission network so that you can aggregate diverse resources in terms of loads and generators and take advantage of those sort of network effects. So I think that is a really strong thing, and that you'd want to be able to take advantage of that as much as you can. There are some things that are clearly some things on the cost side that are long-standing. So you can reduce the cost of this asset, and again, with some of these things like the DC coupled options, you can have some of this clipped energy that would otherwise be wasted that you can then sort of shift and deploy out to the system at later times. So by having that asset there and available and somewhat maybe participating in that sort of portfolio, but then also available to do things right at the plant level, you might be able to have some additional advantages from that perspective. So I think it's good to have both of those perspectives in there for sure.
And I think one final question before we get to our last panel. What improvements are utilities making to modeling, say, an integrated resource planning for resource adequacy to better incorporate storage standalone or in terms of hybrid plants? Because hybrids are rapidly increasing, but we haven't had them for that long. And so I'm just wondering if utilities have played catch up in terms of how they're addressing their resource adequacy benefits in their modeling.
I would say that one of the things, I would agree that there is not a lot of experience with this. There's not a lot of clear best practices, and so I think the utilities in often cases are sort of forced to somewhat improvise on the fly. And so, but I think that when you look at some of the examples of utilities that have been doing this, one of the things you see is that on the resource adequacy side, you'll often see that the way that they calculate the contribution of a hybrid asset might be just simply to take what you would have of the standalone storage asset and do a capacity credit calculation of that, and then add to that the capacity credit of what you'd get from a standalone renewable resource. And both of those things, I think we're sort of coalescing on methods for doing that, and those are pretty standard by now. And then you would just simply sum those two up, but then you would cap it at any sort of shared infrastructure. And if you look at some of the results that we had from a more detailed model, that's not a bad approximation. I think that what you want to look for are those kind of cases that might catch you by surprise. Again, sort of that winter peaking utility, that was something that kind of caught us a little bit off guard, that you would actually see that reduction. And I don't think that there's a lot of tools and methods that have been used yet to kind of capture that. So I think there's a little bit of catch up to be done there, or at least some best practices to be established and disseminated.
But that proxy method is a good start. That makes sense to me.
Yeah.
All right, well,
again,
thank you both. That was, go ahead, please.
Oh, I was just going to say, it lines up well with what we saw with, again, kind of more detailed analysis.
All right, thank you both. I thought that was a really good session, very informative, lots of topics. Turning it back to you, Carrie, for our last session of the day and the last of the training.
Thanks,
everybody. And a reminder
Thank
about surveys, I'm sure. Thank you.
Thanks.
Bye.
Thank you both. Lisa, you know me so well, you know what I'm going to say. I am going to drop the links for the evaluations in the chat box for everybody. Second to last time, we are getting ready to hear from Doug Black and his other colleagues at LBNL, Jason MacDonald, and then after their presentation, Michael Kintner-Meyer from PNNL will be joining us to wrap up the day. And I've seen Michael speak a few times, so you want to be here for that. So Doug, can we get a sound check from you? Great. We cannot hear you.
There we go. Okay, got it. I didn't realize I had control. I thought that you had control over that. All right, great. Well, thank you very much. So we're going to be talking about planning for electric vehicles and strategies for managing the charging of those vehicles. As mentioned, I'm from the Berkeley Lab, as is my colleague Jason MacDonald, and Michael Kintner-Meyer is from Pacific Northwest National Lab. Next slide. So a quick high-level overview of what we're going to go over today. We're going to talk about why this is important and provide some examples of current and future EVs and EV charging stations, present some considerations from a grid planning perspective, some examples of investments in charging infrastructure, a discussion of forecasting methods, algorithms, and some of the current work in that area. A bit on existing forecasting tools that can be used for EV charging load. An example of utility planning, and we'll leave you with some questions that you can ask in planning for transportation electrification, and some resources, and then we'll have a Q&A. Next slide. So the major driver here is in reducing greenhouse gas emissions. There is a drive to replace fossil fuel-based vehicles with electric vehicles. To meet those goals, we'll need EVs at such a level that charging them will put gigawatts of load on our existing grid. A particular challenge to this relative to current electric loads, such as residential, commercial, and industrial, is that EV loads can vary both in when and where they occur. This challenge, though, also presents a great opportunity because this variability can be used to our advantage in minimizing the impact on the grid and minimizing or reducing the cost of that infrastructure to support that load and by shaping or incentivizing the time and place that vehicles charge, and not only reduce the impacts, but also provide benefits of flexibility and services that could benefit the grid. To give an example of the type of load increase we're looking at the residential level, level 2 charging station, which is a faster charge and is growing in utilization in homes, represents a 6 to 12 kilowatt load, which is comparable or exceeds in any residence. And the total amount of energy that will be consumed to charge vehicles at a home is forecasted to represent 25 to 45% of a residence's annual energy use. To drill down a little bit more in the ways that EV loads differ, EVs are mobile. They can charge in different places. We'll go over some of those locations. And not only can that charge vary between different EV owners and their EVs, but even the same owner and EV, their charging load can vary day to day, different days of the week, different seasons. And another critical aspect here is to get the flexibility to shape these loads, to provide incentive or create rates that make it appealing for EV owners to allow their vehicles to be used and allow their charging patterns to be changed. You have to compete with the critical value of providing that mobility. Next, I think we're going to go to a poll now, or no, after this slide, I guess. Oh no, there we go. Okay, so how do utilities in your state treat EV load in distribution system planning? And EV loads are added to other load growth and DER assumptions. EV loads are uncertain. Utilities develop many scenarios, or charging management is addressed through scenario analysis. Okay, and it looks like we're pretty evenly split between EV loads are added to other load growth and DER assumptions, and utilities use many scenarios, with charging management being used in scenario analysis much less. Okay. So a quick overview of current EV availability. I think you're all familiar with EV sedans that are available, that have been for about the past decade. Nissan Leafs, the Tesla line, Chevy Bolt. There are some plug-in hybrids as well that have smaller batteries because they have a small gas engine to supplement. Currently, there are no OEM light-duty trucks or minivans. There are plug-in hybrid minivans, but there are plans and proposed makers have these in the works as well, and they'll have about the same size batteries. At the medium-duty level, so we're talking about delivery vans, work trucks. There are some makers entering this space. There is some availability, but it is limited. A bit larger battery sizes. Probably the most noteworthy here is the recent news of Amazon's order for 100,000 fully electric delivery vans. On the heavy duty side, transit buses, there are a couple different makers that are operating in the U.S. They are mostly at pilot scale, some operating in normal operation, but definitely out there being produced, and again, limited, but we're seeing it. Long haul trucks, there's interest in it. The work has begun. Battery size will be very large. They're not quite on the road yet, but there's a drive to get them soon in the future. Some of the important considerations here are, as battery costs decrease, the battery sizes will increase in vehicles, especially in light duty vehicles, in which there's a concern about, and the other sections as well, but where there's the concern of range anxiety. So to alleviate that fear of running out of charge, as these batteries get larger, the charging patterns will change too. With a smaller battery, let's say I had to charge every day, you can count on kind of that charge every day. A larger battery, maybe someone charges every other day, once a week, and so there'll be we'll need to look at those changes. Autonomous vehicles, driverless vehicles, which may be a little further out, but will also change charging patterns, because they'll want to minimize the amount of time that they're sitting, so there'll be less ability to move their charging load around, because they'll want to be on the road and not sitting and decreasing their charge amount. Next slide. Next slide. So locations, Residential charging, very common. Workplace charging is growing. Public charging is a little more nascent. Another place that should have been listed here is fleet charging, depot charging. And the types of charges in each of those locations. Residential can use both level 1 and level 2. A lot of residents could use just level 1, which is a standard house outlet. Some workplaces just use those standard outlets as well. Mostly though, workplaces, commercial, public are going to use the level 2 chargers, which range from 3 to 19 kilowatts. The fast chargers are used for quicker fills for travel, so you'll see them on transit corridors, more like gas station type of charging locations. Also used by fleets though as well. Powers 50 to 350 kilowatts. The next generation of extreme fast chargers is targeted more at the larger vehicles, heavy duty bus, and trucks, and can be 400 kilowatts plus. Some of the higher end light duty though are looking at Porsche uses a larger charging power. Next slide. And finally, I'm just going to wrap up with making a point about being in the early stages here of EVs and EV charging equipment, that there are a lot of different charging standards and different vehicles using different charging connectors, meaning that EV infrastructure and charging stations have to consider what EVs they'll be charging and what connector they'll need. The most common is up in the upper left, the J1772 level 2 type charger, type connector. Tesla could also be considered fairly common due to the number of Teslas on the road and the number of stations that they've installed along transit corridors to support their vehicles. CHAdeMO is another common one. Nissan Leaf, other foreign makers use that standard. And what's growing for fast charging here in the US is the CCS combos, both 1 and 2. And now I'm going to hand it over to Jason MacDonald.
All right. Thanks, Doug. So I'm going to jump in and talk about ownership models for charging infrastructure. The way I've been thinking about this ownership models is kind of who funds it and who operates it. There's the same sort of large categories of actors, utilities, or the private sector, or individuals' residences, and then public sector might all fund these or provide some measure of funding for infrastructure. And then we'll talk more about utility in the next couple of slides, but just to give you a flavor of the private and public. So in the private sector, you can have kind of the vertically funded and operated approach, like automakers like Tesla and Volkswagen, who bought their own charging and created their own networks. Or you might have things like a retail chain who puts in charging infrastructure, but for their customers, but would like a charging services company to manage that infrastructure and allow them to recoup the cost of their electricity using their network, and so connecting to a charging network in that sense. And that's the same can be true of office buildings, where they might be providing for free charging, or in some way providing charging for their employees, but could also be working with a charging services company. So it could be multiple actors in a funding and operating kind of structure for the private sector. In the public sector, similarly, we could have this multiple actor kind of version where maybe a municipality puts in some charging, but then connects it to a charging services company and has them operate for them. The other way that is commonly some charging infrastructure is funded is through rebate and pilot programs that may be supported by the state or other government agencies. Something to consider when we're thinking about all of these is there, since assuming that we begin with the assumption we want to bring this EV charging load, assuming we want to bring this EV charging load, are we providing adequate incentive through rebate programs, or is there already adequate incentive through the demand for charging to get this infrastructure in place? There's always that chicken and egg problem between charging infrastructure and the EV demand. And then in the utility case, can they rate base this charging infrastructure, specifically charging infrastructure, or just the wires and things to get to it? Let's go to the next slide. So in a lot of states already, there's EV or utility ownership of EV infrastructure. We've got quite a number of states. This map coming from Bloomberg. And already even some in the Midwest, with Michigan being, it looks like the second darkest of the states. California has a very significant amount. Next slide. So drilling a little bit more into utility ownership models for EV charging, you can kind of think of it in the sense of what it takes to get those electrons all the way to the vehicle and how much of that is being paid for by the utility. So in the business usual case, of course, it stops at the retail meter at the host site, and that's where that's the last place that the utility is invested in. And in a completely utility owned and operated case, they would, provide all panel upgrades or anything else beyond the meter that's required, maybe trenching or new conductors, and then additionally buy the EV chargers and put them in place. This obviously has benefits. The utility can identify any negative impacts, grid impacts. It speeds deployments, as they can remove as many barriers as possible to getting connected. But it can crowd out private investment and lead to possibly higher overall costs and maybe have difficulty keeping up with the changing technology and customer preferences. Another version of that might be that the utility provides all the infrastructure needed except for the charger, or near to all the infrastructure needed except for the final charger itself and the EV specific infrastructure. So they're doing all the things that they're usually very good at. And this also would speed deployment of charging and increase electricity sales, getting more EVs in, but it also is leveraging private capital, getting the host site to put up some of the money. And of course, you can always do the rebate program style incentives, where you're providing incentives for all the different steps that the host site might be needing to do. So next slide, I believe this is a poll. So here, what are the key drivers for utility investment in EV infrastructure in your state? And select one of the following. Utilities can rate-based investments in charging infrastructure. EVs will increase kilowatt hour sales and utility revenue where the rates are flat, and EVs will provide options for grid flexibility and renewables. Excellent. So, wow, also a pretty even split between the first two, or exactly even. So it looks like the rate-basing charging infrastructure is the key driver. That's not surprising, and that it will increase sales. So this is mostly around ensuring that their utility is getting enough money. And then, okay, so we'll go on to the next slide now. So ownership models, what we've articulated so far is largely relevant for light duty vehicles. Ownership models that have emerged for medium duty vehicles and heavy duty vehicles kind of fall into two categories. The first is kind of the obvious one. The EV infrastructure is owned and operated by the fleet owner. So the second is different, where there's a third party that leases that infrastructure to the vehicle fleet, and that might be the charging station suppliers might be leasing them. Vehicle manufacturers themselves might be leasing those things. It could be the turnkey systems from your typical electricity infrastructure equipment manufacturers, or it could be coming from like the charging services network providers, the charge points and eMotorWorks and EVgo's of the world. Next slide. I'm sorry, next slide. Great. So, no, sorry, I made you go too far. It's that, yeah, go back to the next slide, sorry. I'm trying to get to, yes, the managed charging and utility rate design. So moving away from ownership, now how do we manage the charging infrastructure or managing the charging load once it's there? What's been successful so far is the time of use rates, and they've been implemented all across the country. Things to consider here is what you're applying that EV specific or for EV owners time of use rate to. Is it to the whole home? As we pointed out before, EVs are definitely the largest single appliance that any homeowner would have, and so the engagement in time of use through an EV can have impacts, and especially if they're on the same time of use schedule, can have impacts on the rest of the house load as well. Or is this time of use rate applying to the EV only, in which case you need a sub-meter or a secondary meter? Or in some cases, the utilities have chosen to allow the native metering infrastructure already built into every charging station, or most charging stations, I believe, to provide that sub-metering to the utility. So here I'm highlighting an example residential rate, this one from PG&E, and what I want to point out here is there's a pretty large difference between off and on peak, roughly 3.5 to 4 times the price difference between those two, and that the off-peak period starts at midnight. That should be midnight. It says 12 p.m. And what that has the potential to do is kind of shown in this figure here. There's what in this figure is a travel survey based, I believe, model of electric vehicle charging, assuming the charging equipment that exists at home. If you look at the level 2 charging, there's a peak if unmanaged around 7 p.m. And then if you instead defer all charging for a period which is easy to do and would happen with a time of use rate, that peak in aggregate from a lot of different vehicles, this is multiple vehicles, can be up to 4 times as high, but it'd be at midnight. So there's the risk that you create this shock to the distribution system that should be managed. This is once the EVs are at scale, and this is only EV load. For commercial, it's important, or the thing that can be challenging about EVs is demand charges. And so one innovative approach that PG&E also has recently passed through the regulators in California is this idea of creating a subscription model to demand. Rather than having a demand charge directly, you subscribe and pay a monthly fee associated with the amount of demand that you intend to have. And that's likely either with a penalty if you go over, or be revisited every time that you do go over. And then the last method of managed charging isn't through a tariff. Instead, it's through traditional demand response programs, where in the time of need, the utility or the operator can send a signal for curtailment of charging, or even a KW command, and to get the desired result. There's few examples of this at this point. There's been a few pilot programs in California, but they have led to they were successful enough that they've led to standardization of ensuring that there's communication to EV charging in California in the future. Next slide. So this next slide is just trying to highlight a few examples of effective TOU rates that you can go and look into. The big takeaway here is that all of these rates were successful at getting moving charging into the off-peak period. And then there's also a description of one of the demand response programs that were done in Southern California as well. Next slide. And the last thing before I hand it over to Michael, here I want to hit on a few key issues that we need to be thinking about when we're doing planning for distribution planning with EV infrastructure in mind. First, of course, is when you're going to receive this this new demand, and then also at a high level, how much of that new demand at each year you're going to get, or how much of the EV infrastructure is going to be put into place. And this is all, you can get to this kind of information through EV adoption modeling, and here we list a few of the things that impact that modeling, the modeling results. And then the second thing you need to think about once you know how much charging will be there is what the charging profiles will look like based on the travel that you might see in your jurisdiction. And so again, we've highlighted a few modeling software that exists, or those that are looking into it, and then also there's also historical data out there to support that. But there's a question about how useful that is for future as the technology is changing so rapidly. The last thing to consider here is where in the distribution feeder you might receive or might get this charging, and this is tougher. There isn't as much modeling out there. Some survey data and some modeling, mobility related modeling that might articulate what travel corridors would likely have the most need for EV charging but that's largely been applied in urban areas at this point. And we can move on and give it to Michael.
Good afternoon. Next slide, please. Yeah, so this is addressing now the when. So we talked about the when, the how many, how are they being charged, and where are going to be charged. So the when addresses years, where utilities are interested in, from my service territory, how much do I really need to assume from a bulk power perspective and from a resource adequacy. And so this is a study which is a little dated, 2017, but it still holds the best information from a national perspective. So you're seeing here for light-duty vehicles, cars, SUVs, vans, and pickup trucks, penetration curves. So this was done by EPRI from the county level up. So it used historical trends and then projected it up into the future, given certain adoption rates. Most people use actually not only the medium, but go straight to the high scenario, which you can see here in the green curve. Next slide, please. So when it comes to the underlying information, you're seeing here some historic sales numbers there, which are subject for this estimation there that you just saw in the previous slide. And you're seeing is the growth from a regional basis has primarily been taking place in a U shape around the coast there, with Texas there in the middle. Michigan has some here. It's not on it, but has some penetration as well. But the interior there is lagging a little bit, and we're hoping that they will catch up as well. Next slide. So now we're looking at some of the key driver, at least in the past, and they have been subsidies. Foremost, the federal tax credit, and they are such that manufacturers up to 200,000 vehicles can get up to, owners buyers of electric vehicles can get up to $7,500 per vehicle, up to the manufacturer's sales of 200,000. Then it will be reduced to half of that amount, and then a quarter to that amount. And so for Tesla and General Motors, they actually fully subscribed to the available federal tax credits. Tesla in January 2020, and I think GM in February. So if you buy a Tesla, if you buy a GM, you don't get a federal tax credit. On the state side is we also have seen a tax credit, not quite as generous, but still considerable. And so they're being added on to it, and they together can make a substantial impact by reducing the cost of a vehicle by $10,000 in some cases. Next slide, please. So here's another driver, and that is simply mandating the change from internal combustion engines to electric vehicles. And California is ahead in the regulations of EVs. And you're seeing here some medium and heavy duty vehicle mandates as mandated by the California Air Resources Board for truck vehicles starting 2024. And you're seeing here the progression. It's particularly relevant for buses, and we're seeing already that bus transit authorities such as LA Metro with over 3,000 buses are already underway with changing out their vehicle fleet to electric vehicles. So this means significant amount of investments from these transit authorities and at a fairly rapid pace. Furthermore, not quite a month ago, the governor of California banned in executive order the sales of gasoline vehicles by 2035. So this is exactly the date when Norway also declared to ban gasoline-driven vehicles. Actually, they broadened it to all vehicles in Norway, and you're seeing other countries, in particular municipal jurisdictions, London, Stuttgart, and European states have already also declared a ban on internal combustion engines. So this is coming. As far as vehicle infrastructure is concerned, there's an interesting bill there that requires California and the California Energy Commission to actually project what would be the necessary infrastructure for mid and heavy duty vehicles, such that this chicken and egg problem that Jason was talking about can be omitted. So when these vehicles have to be purchased, that there will be sufficient infrastructure available for these vehicles to drive and to function. Next slide, please. So you're seeing here another projection there by Bloomberg. They're very into projecting there with lots of analysts on their staff. So you're seeing here for the US as a whole, passenger vehicles, commercial EV vehicles, and then fleet buses. As I mentioned there before, California is really pushing the transit bus concept, being electrified, but other organizations, King County Metro in the Puget Sound, Seattle area, are also moving very aggressively, and elsewhere in the nation, you're seeing that transit authorities, particularly from an indoor from an air quality perspective, are revamping and replacing their diesel fleet or natural gas driven internal combustion engines. You're seeing here other fleets are not going quite as aggressively, but still a fairly rapid increase that we're expecting over the next few decades. Next slide, please. So now we're switching over from the when to actually the how. How are these vehicles being charged? And that's looking at the load profiles of electric vehicles. And so you're seeing here on the left side, light-duty vehicles, different charging profiles, and that are predicated on different assumptions of where electric vehicles are being charged and what the use patterns might be, and some of the control strategies that we already have seen emerging. And so you're seeing here some outputs from NREL's EVI Pro. It's publicly available. These charging profiles, which is probably the most authoritative that there are. It looks at really a composition of different scenarios intertwined there with some dominance, as you can see here, home, low, that is low capacity or low charging rate, no delay, and then with delay. So various options. We looked at it from a grid impact assessment perspective, and we're seeing here that this orange line there with a peak at 1900 hours is probably the one that would be most taxing and most stressful for both the bulk power as well as for the distribution system. On the mid-duty and heavy-duty vehicles there, these are some scenarios that PNNL developed for a recent analysis. We estimated for the mid-duty vehicles sort of a delivery truck vehicle-like operations with a use case such that the vehicles are charged overnight. So you're seeing here no charging during the day. The vehicles will be used during the day, and then at night will be charged. The heavy-duty vehicles, they don't have a home, so they will be driven along the highway network of the United States, and then picking up load and dropping it off. So we developed a model that simulates these driving behaviors, and you're seeing there much flatter load there because these trucks are being used 24/7 with some episodical peaks there, which are incurred when vehicles stop at major interstate highway truck stops and concurrently charging. So there are two key messages that this actually entails, and it's not included quite in this slide. And that is, if you aggregate the light-duty vehicle with the mid-duty vehicle and the heavy-duty vehicles to look at the composite, say for 2025 or 2030 scenario, from an energy perspective, the most electric energy will go into light-duty vehicles, simply because by numbers. Those are the ones that are around for the last 10 years, and they will be growing very rapidly. But if you look at the distribution system, from a distribution system perspective, the most taxing may actually be the mid and heavy-duty vehicle. Why? Because the charging currents are much higher for these vehicles. So the charging stations are much larger. On the heavy-duty vehicles, you saw in the previous slides, 500 plus kilowatts. There's currently research underway for not only the Tesla semi-truck there, which allows charging rates up to 2 megawatts. There's also a Daimler North America under the Freightliner brand, as well as PACCAR or Kenworth trucks that go clearly over 1 megawatt, 1.5 megawatt charging rates. So those will be pretty much rates there that we can expect per vehicle. And these are tremendous charging rates there if you think about several vehicle charged at the same time. Next slide, please. So now we're looking at some concepts of how you manage this load. And there's a lot of interest in it because it directly relates to the hosting capabilities of infrastructure. If you allow to manage that load, or if you utilize the flexibility of these loads to the degree that they exhibit them, you can smooth out that load profile that you saw there previously. So when we talk about flexibility, we need to differentiate the flexibility in two dimensions. One is temporally. So if you come home, you may not charge right away. You have a timer in the vehicle, and you say, wait until a later time at night and then start charging until the morning. But there could also be a spatial dimension to it. You might say, you know what, my employer offers a charging at a much lower rate. I'm now so low that for a fixed price, I'm better off just wait until the next day, and then I go to work and charge there. So there's a flexibility with respect to not charging at home, but charging elsewhere. And so the question now becomes from a grid planning perspective is, how do you now use this? Where do you get data for this flexibility? And the answer is, it's difficult. It's difficult. So we're looking at basically at different ways there. You can either cap the load so that you don't go over a certain peak, or you basically schedule the energy in blocks and you move it along such you will never exceed a certain threshold. And then, of course, what you can do is you can augment it and offset some of these peaks there with distributed energy resources right next to the charger. Next slide, please. Oh, this animated. Yeah. So another challenge there is in looking at how it's being charged relates to the driving patterns. Very little is known how people drive. I can tell you is we have a staff who has the same vehicle that I do, has the same distance to the laboratory. He charges totally differently than I do. And so this is personal preference. How do you do the charging? So what we're seeing now is that more and more of the mobility and the transportation modeling are being utilized to address these different use cases, particularly as the battery grows and we're getting more flexibility in terms of how we charge, where we charge. With a Leaf that has about 60, 70 miles range, I need to charge every night at home. If I had a Tesla with 300 miles range, I may not. And I have more flexibility. And so what people are now doing is they're looking at urban mobility modeling, and then look at particularly the new mobility as a service opportunities, electric taxis. How would they actually utilize an electric vehicles? When would they charge? What are really the common sweet spots in the transportation system that overlays with the availability of electric capacity there to find some sweet spots for erecting a charging station or placing a charging hub. Next slide, please. So we're seeing another way there, how we might do it actually from a fleet perspective. So if I had several vehicles, and this becomes very, very important from a transit fleet perspective, there's already voices being raised. I'd like to have optimal charging capabilities as my vehicle park grows. So I'd like to be able, as you can see here, buses or vehicles having different state of charge. On the left-hand side, you're seeing A, B, C, and different times when they start and when they come back. And rather than letting them charge based on some schedule that is an outcome of the driving pattern, which may actually increase the concurrent charging there, as you see here on the bottom left. In the power requirements A, B, and C, at certain times there are 3 are being charged. What you're trying to do is stagger them out in time, again, if you have the flexibility to reduce the power requirements. And so this is something that fleet owners will look more and more into it. The challenge now is what are the charging requirements, what are the communication requirements to buy something today that in 10 years, when the last bus will be replaced, is still valid. Next slide, please. So I'm coming here to the last slides, and that's addressing some of the steps from a distribution planning perspective of electrifying vehicles. And so the key question is, when do we need to upgrade which circuit to which new load requirement, given all the other changes in the distribution system, i.e. load growth or deployment of distributed energy resources, the way you heard from Jeremy and Andrew Mills. So the first thing is for light duty vehicles, and I'm splitting it between light duty vehicles because there are methodologically some differences, and you will see this in a moment. So for light duty vehicles, step 1 is EV adoption. And the question is not only in what year will you have in your entire service territory how many vehicles, but you also need to know is where will they actually be on the map. So when you have your distribution planner with his or her GIS system that sees where all the circuits are and where all the customer nodes are, that you understand is where the vehicles will actually impinge upon your electric infrastructure and add load. So that is, it's a challenge. And so there are some utility companies that are looking at socioeconomics there with disposable income, certain purchasing decisions, and see, for instance, where vehicles actually being deployed, and work off of that in a socioeconomic econometrics framework. And then the question becomes, okay, so what's the load profile? Again, if you have a Tesla, do you charge the Tesla every night? Do you charge the Tesla at work? Where do you charge it? And how fast would you charge it? Then you superimpose the new EV load, do a power flow analysis, add all of the other assumptions to it for a certain time horizon or study horizon in the future, and out comes voltage violations or thermal load exceedance, which now induce you to think about how do you mitigate this. And so the first thing is probably, and the lowest cost strategy is utilizing the flexibility. Can you induce somehow the vehicles to be charged at different times so you don't have this concurrent charging? And so time of use might be something, but when it comes to 3 Teslas at every house, we have some of these things in Queen Anne's in Seattle, old infrastructure. You need to really get at the individual vehicle and stagger the individual vehicles. So how would you do this? You need to have some load management control strategy. And then how do you use PV or smart inverter for voltage issues or storage? Or do you need to, does it not help and you have so much more growth there in other areas with new home developments there and you're going straight to distribution upgrades? Next slide. And that's the final slide here on the mid and heavy duty vehicles. It's a different approach. So this is, rather than trying to look at historic data, there aren't any historic data. And so we've seen an approach that actually DT Energy in Detroit has done is they actually really did some survey of commercial industrial adopters. They looked at top view, let's filter out which one of my commercial industrial customers have large fleets. and which ones are then likely to replace their diesel vehicles or gasoline vehicles with electric vehicles. And so then they pick up the phone and talk to the fleet managers. Usually the fleet manager is not the person that they actually have dealt with, because the fleet manager deals only with gasoline or diesel, not with electricity. But that's one approach to really get a sense is, are there in the plans a switch over from fossil fuels to electricity? And then you're doing really dedicated what-if scenarios for this additional load. You need to discuss some of the use patterns, how these vehicles are being used, where they're being charged. Can you move a charging station from the depot charging opportunity to outside locations where you might distribute the burden a little bit? And then you're doing power flow analysis and looking again very similarly as in the previous approach at mitigation strategies. And with that, I'm handing it back to Doug.
Thanks, Michael. Next slide, please. Okay, so all of what's been presented really comes down to it is summarized in these questions that should ask utilities in how they're doing their planning. So I'm just going to go over the top level of each, and then they'll be available in the slides, just in the interest of time. So first, the question deals with how EV adoption, EV growth is being forecasted or predicted. What are the assumptions being made? And that's going to vary between light duty vehicles, medium and heavy duty vehicles, and even the different types within some of those categories. And then given the assumptions of how EVs will grow, what impacts does that have on EV charging? And again, the different charger types for each of those classes. Next slide. And given the infrastructure, how do you estimate what the EV load will be and where? And for distribution planning, how do the utilities treat that load? This was similar to one of our poll questions. Is it load growth or assumptions, developing different scenarios? Is near-term planning considering the trajectories to meet long-term goals? And then finally, what are the key drivers? Another poll question for utility investment, rate basing, sales, and opportunities for control. And our last slide just provides resources for more information. These are links to a lot of the references in the materials within the talk. I do want to point out the last two are very good general resources, or more than general, of a broad array of very good information. The Department of Energy provides an alternative fuels data center, new technologies, developments in EVs, EV charging standards, costs and benefits, the incentives, regulations, rules for each by state, and then the California Public Utility Commission ZEV website is great in that it just covers everything that body is doing to address this in California, which they're already dealing with pretty good numbers of EVs, and the trends are large, and so there's a lot of work happening there and a lot of great examples that you might want to look for. And with that, we'll go to questions.
Sure. So for right now, I just have one question. If we can actually flip to your appendix slide 36, the last one in your deck, you have some graphics on grid architecture and the role of the aggregator, and I think that's a hot topic right now. So maybe you could just speak to this slide if you're able.
Okay. So it's really looking at, a lot of what we've talked about comes from the utility perspective, but in a lot of ways that we try to do demand response and provide grid services and provide energy efficiency. We have aggregators do this, so a third party. They can, in the same role that they play in those other types of services, the same can happen here with the EVs. And we've done some research studies of aggregating up different fleets and different users. BMW has done one to provide these different resources in California, proxy demand resource. We've done actual, ancillary service market participation. This is with specialty bidirectional vehicles. The challenges come with the communications between different EVs and different charging stations and where standards come in. And so that's some of the work that has to be developed for aggregators to be able to fill that role, but similar to utilities as well. So I hope I've kind of, that covers it.
Yeah, that was a great overview. I really appreciate that. Well, thank you, Mr. Black, and your team for your training today and your time to put this together. I think we're going to move into our next steps and wrap up the training. So thank you.
Thank you.
Great. So thank you all. Thank you for sticking it out until the end. If you're on Eastern time, it's almost 5:30. So if you have joined us for all 3 days, you are eligible for a certificate of completion, and you will be able to receive that through my colleague, Dominic Liberator, and he's been emailing you throughout the week, and he will email you more links or the same links to the evaluations. We would really appreciate that information. We hope you enjoyed today's training, and but either way, we would really like your feedback on how to make the most of this training for the future region. So as you know, this came around to your region 2 years ago, so if you were there, you can see how this is different, and we really did take your suggestions. So please do take the time to find those evaluations and provide us that valuable feedback. Other than that, I think we will close it out, and thank you all for your participation. We will hope to see you virtually soon.